Deep in the heart of the universe, light is behaving in ways it shouldn't. From the powerful quasars, distant, supermassive black holes, comes a strange signal, one that seems to defy the laws of physics. Their spectra appear inverted, as if the very fabric of reality is being twisted. What could cause this cosmic anomaly? Is it a flaw in our understanding of space, or is the universe hiding something much deeper, a secret we've yet to uncover? Welcome to the strange and captivating world of inverted spectra and quasars, where the usual rules of astrophysics bend, and our cosmic assumptions crumble. But before we continue, subscribe to the channel so you don't miss out on any of these videos. This isn't just about a few anomalous wavelengths, or a slight calibration error in a telescope. This is about entirely reversed energy distributions, signatures of light that should be absorbed but appear as emissions, and emissions that should blaze brightly but are inexplicably missing. It's as though some quasars are broadcasting their existence through a cosmic funhouse mirror. And the implications? They might upend what we think we know about black holes, intergalactic matter, and even the fundamental structure of space-time. But what are quasars really? And how can their spectra, essentially the fingerprint of their light, be turned inside out? To understand this paradox, we must travel deep into the heart of galaxies, into the very regions where matter spirals into monstrous black holes at velocities approaching the speed of light. Quasars, or quasi-stellar objects, are among the most energetic and distant members of the known universe. They are powered by accretion disks, immense, swirling funnels of superheated gas and dust collapsing into supermassive black holes that sit at the cores of ancient galaxies. When these cosmic engines are active, they unleash torrents of electromagnetic radiation, far outshining entire galaxies and reaching us across the cosmos as brilliant, compact points of light. Under normal conditions, when we observe a quasar, we expect its spectral lines, those unique light signatures of different elements, to follow predictable patterns. The energy output from these objects is so immense that the surrounding material becomes ionized, producing strong emission lines in the ultraviolet and visible spectra. These emissions can tell us about the quasar's chemical makeup, velocity, distance, and even the environment it inhabits. But in some rare, perplexing cases, these expected signatures behave in strange, seemingly contradictory ways. Inverted spectra appear, spectra where the light is absorbed where it should be emitted, and emitted where it should be absorbed. It's not just unusual, it's deeply unsettling to cosmologists. It suggests something is happening in the environment of these quasars, something exotic, possibly unprecedented, that reshapes how light travels and how matter interacts in the most extreme conditions the universe can offer. To grasp how this inversion occurs, we need to detour into the mechanics of spectroscopy, the science of analyzing light. Every atom and molecule absorbs and emits light at specific wavelengths, like a barcode. When light from a quasar passes through various gas clouds, whether near the quasar itself or in intergalactic space, it gets absorbed at those wavelengths, leaving dark lines in the observed spectrum. Conversely, when atoms in excited states emit photons, they create bright emission lines. It's a cosmic ledger of energy transitions. Now imagine this process turned upside down. Picture a quasar that, instead of showing bright hydrogen emission lines, presents us with deep absorption features. Or iron lines that appear in the exact wrong position, or worse, reversed in strength and structure. Scientists first noticed these puzzling cases decades ago, but recent surveys using the Sloan Digital Sky Survey, SDSS, and other high-resolution instruments have uncovered dozens of such anomalies, each defying the typical models of quasar structure. One proposed explanation involves line-of-sight effects. Perhaps the light from the quasar is passing through unusually thick or ionized clouds of gas, creating absorption features that mask the emissions. But this theory quickly runs into problems when the depth, shape, and pattern of the absorption lines don't match any known foreground material. Others speculate about the role of relativistic jets, spewing particles at near-light speeds, potentially distorting the observed light in unexpected ways. More radical hypotheses suggest that gravitational lensing, where massive objects bend light around them, could be involved, magnifying and distorting the quasar's light to such an extent that its spectrum becomes warped. And yet, lensing effects usually magnify and duplicate images, not reverse spectral signatures. Could it be, then, that some quasars have intrinsic properties that generate these inverted spectra? Could there be a class of quasars fundamentally different from the rest, whose internal magnetic fields, disk dynamics, or chemical compositions create conditions where light interacts with matter in previously unimagined ways? It gets stranger still. Some researchers believe that these inversions may be the signatures of exotic particles or quantum effects on a cosmic scale. If light is being altered or filtered by unknown mechanisms, perhaps related to axion-like particles, dark matter halos, or even quantum gravity, then inverted spectra could be our first observational clue that the laws of physics, as we know them, begin to shift in these extreme environments. And let's not ignore the possibility, however fringe, that we're glimpsing technologies far beyond our own. Some of the most speculative papers hypothesize that inverted quasar spectra might be artificial, or the byproduct of non-natural energy manipulation at galactic scales. While these ideas remain in the realm of science fiction for now, the simple fact that such theories are being entertained underscores how little we truly understand about what's happening in the hearts of these mysterious beacons. And then there's the temporal component. Because light takes billions of years to reach us, we're not observing quasars as they are now, but as they were in the ancient past. That means some of the inverted spectra we see might be snapshots of transient, or evolving processes, brief phases in a quasar's life cycle that aren't common, or easily repeatable. In this sense, the inverted spectrum may be a rare, transitional signature, one that appears only under highly specific cosmic conditions, making it even more crucial for astronomers to analyze, catalog, and interpret each case with utmost precision. As more quasars are observed and more inverted spectra come to light, astrophysicists are beginning to realize this isn't just a quirk or a mistake. It's a message written in light, one we haven't yet learned how to read. Every wavelength, every flipped line in the spectrum, is a puzzle piece. Together, they might reveal something about the evolution of galaxies, the behavior of matter under extreme gravitational and magnetic stress, or perhaps the next frontier of physics itself. And so, we begin a journey not just through space, but through a cosmic mystery that challenges the very nature of observation itself. What follows is a deep, expansive exploration of everything we know, suspect, and wonder about inverted spectra in quasars, from the foundational science to the latest theories, from the edges of observational astronomy to the realms of speculative physics. Buckle up, because once we fall into this rabbit hole, there's no coming back the same. To understand this paradox, we must travel deep into the heart of galaxies, into the very regions where the most extreme physical processes in the known universe unfold. At the center of many galaxies lies a supermassive black hole, a gravitational behemoth with a mass millions or even billions of times greater than our Sun. These titanic entities don't merely sit quietly. When conditions are right, they erupt into brilliance, pulling in gas, dust, and even stars. This material doesn't fall straight in. Instead, it forms a rapidly rotating accretion disk that heats up through friction and magnetic turbulence, emitting staggering amounts of energy across the electromagnetic spectrum. These luminous beasts are what we call quasars, short for quasi-stellar radio sources. And despite their point-like appearance in the night sky, quasars are anything but small. They outshine entire galaxies. Their light travels billions of years across space to reach Earth, carrying with it stories from the early universe. But here's where the puzzle begins. When astronomers split this light into its component wavelengths, something seems wrong. The spectrum of a normal quasar typically shows emission lines, bright spikes in certain wavelengths, caused by elements like hydrogen and helium being superheated and emitting light. These lines act like a barcode for the chemical composition and energy processes happening near the black hole. But in certain cases, scientists observed something that didn't make sense. In these rare quasars, the lines appeared flipped. The emissions were missing. Absorptions were inverted. It was as if the energy had vanished or been replaced by something that mimicked its exact opposite. This wasn't a simple calibration error or an observational hiccup. The inverted spectra appeared repeatedly, reliably, and in multiple quasars across different surveys. The first signs emerged in the 1990s, when data from the Sloan Digital Sky Survey (SDSS) and others began to show strange discrepancies. Some quasars showed absorption lines where emission lines should have been. Others had profiles that didn't match any known astrophysical models. Spectral lines were shifted or reversed, and their intensity patterns defied expectations. It was as if the quasars were cloaked in some veil that was interfering with or distorting their true signal. The immediate response from astronomers was caution. They questioned their instruments. They checked the data reduction algorithms. Could it be an error in the way the light was being captured or interpreted? But the anomalies persisted even under scrutiny. More importantly, they appeared in multiple independent datasets. That was the turning point. Scientists realized they were facing a real, physical phenomenon, one that might hint at new physics or unknown cosmic structures. So what could cause a quasar to exhibit an inverted spectrum? There are a few leading theories, and all of them are strange in their own right. One possibility is that we're seeing the effects of strong gravitational lensing, where light from the quasar is bent and magnified by the gravity of an intervening galaxy or massive object. In such cases, the light path is altered, sometimes so dramatically that the spectrum is distorted. If the intervening object has gas clouds of its own, those clouds could absorb or remit light in ways that mimic an inversion. But even this explanation falls short in many instances. The distortions are too specific, too orderly, to be fully explained by lensing alone. Another, more exotic hypothesis involves relativistic beaming and Doppler boosting. Quasars often eject massive jets of plasma at nearly the speed of light. If one of these jets is pointed directly at Earth, the emitted radiation can be boosted in intensity and shifted in frequency. Depending on the angle, this could cause some emission lines to appear suppressed while others are enhanced. Yet again, this doesn't fully account for the complete spectral inversion observed in some quasars. That brings us to a third, more unsettling possibility: the presence of unknown matter or exotic physics in the environment of the quasar itself. Imagine an accretion disk not composed of ordinary matter but of material governed by different electromagnetic interactions, particles or fields we have yet to discover. These could potentially emit or absorb light in unfamiliar ways, producing the reverse spectra we observe. Alternatively, if the quasar is surrounded by a dense halo of ionized gas or dark matter clumps, these could act like filters, selectively allowing certain wavelengths to pass while blocking others, or even flipping absorption to emission through complex radiative transfer effects. Let's take a moment to understand what makes these inverted spectra so startling. Normally, when a cloud of gas absorbs light, it does so at very specific wavelengths, those corresponding to the energy differences between atomic or molecular electron states. This creates dark absorption lines in the spectrum. But in an inverted spectrum, it appears as though these atoms are instead emitting light at those exact same wavelengths. This suggests a population of atoms or particles that are not just absorbing background radiation, but actively producing photons in precise, narrow bands, sometimes against the expected gradient of energy flow. It's like watching a fireplace that seems to suck in light instead of giving it off, or a prism that makes the colors run backwards. Now, imagine trying to model this in a lab. On Earth, we've never been able to reproduce such inversions under natural conditions. Yes, lasers and masers can produce stimulated emission, which can create bright lines at specific frequencies. But these are tightly controlled, engineered processes. A quasar is a chaotic, thermodynamic inferno. That something so orderly, an inverted emission pattern, can emerge from such a turbulent system suggests that nature is playing a deeper game. It gets stranger. Some researchers have noted that inverted spectra appear more frequently in high redshift quasars, those that lie further away and therefore existed earlier in the history of the universe. This correlation hints that the effect might be tied to cosmic evolution, perhaps changes in the intergalactic medium, the formation of structures like filaments and voids, or even fundamental shifts in the properties of matter over time. If true, it would mean that the laws of physics as we understand them might not have always been constant. That's a big claim. But inverted spectra force us to at least consider it. Then there are the wild cards. Could we be seeing evidence of mirror matter, a hypothetical form of matter that interacts with ordinary matter only through gravity? Or perhaps tachyonic particles, theoretical faster-than-light entities that could interact with light fields in bizarre ways? Some fringe theories even suggest that we're observing echoes from parallel universes bleeding through gravitationally, where the light from a quasar is distorted not just by the curvature of space, but by fluctuations in the dimensional fabric of reality itself. As speculative as these ideas sound, they underscore one important truth: we don't yet fully understand what we're seeing. And that's what makes inverted spectra in quasars one of the most tantalizing cosmic puzzles of our time. These are not just curiosities. They are windows into the unknown, cracks in the facade of our current models, whispering of hidden realms and forgotten rules. With each new observation, astronomers refine their tools, dig deeper into the data, and ask more penetrating questions. Could we be dealing with an undiscovered state of matter? A previously unknown mechanism of radiative transfer? Or are these quasars showing us a fundamental asymmetry in the universe? One that points to a deeper structure beneath what we call space-time. The journey into this mystery has only begun. And as we press onward, following the inverted signatures across the cosmos, we may find ourselves not just rewriting textbooks, but rediscovering the very architecture of reality. This bizarre reversal in the spectral lines sparked a whirlwind of questions. Was it an illusion caused by an unknown interstellar medium between us and the quasar? Was it a new class of object entirely? Or were we witnessing the first signs of new physics at play in the cosmos? Processes so complex and alien that our current models can barely accommodate them? To unravel the enigma of inverted spectra in quasars, we must first understand what a spectrum really is and why it matters so much in astronomy. A spectrum is more than just a rainbow of colors, it's a coded language of light. When light from a celestial source is passed through a prism or a diffraction grating, it's split into its component wavelengths. This breakdown allows astronomers to identify specific elements, temperatures, velocities, and densities of cosmic sources. Every element emits and absorbs light at very particular wavelengths, creating a unique set of lines that act as signatures in a spectrum. In typical quasars, these spectra are rich in broad emission lines. These lines are produced by gas in the accretion disk or nearby regions that is heated to millions of degrees and ionized by the intense radiation around the black hole. Hydrogen, in particular, creates some of the most prominent features, such as the Balmer series. The presence of these emission lines confirms the violent, energetic environments near the centers of galaxies. But when these lines appear inverted, turned into absorption lines, or missing entirely, it throws the entire diagnostic framework into question. What makes the phenomenon so compelling is that it isn't just a single case or an isolated error. Several quasars have now been documented with inverted or highly unusual spectra. In some, what should be emission features are entirely absent. In others, there's a dominance of absorption that seems to contradict the expected outflows and hot gas dynamics. In rare cases, the absorption lines themselves appear in places where no such lines should exist under known conditions. One hypothesis proposes that these inverted spectra may result from extreme intervening material, vast clouds of gas and dust that selectively absorb certain wavelengths of light as it travels across intergalactic space. This is known as intervening absorption, and it's not uncommon in quasar observations. However, this explanation becomes inadequate when the absorption patterns don't match any known configurations of intervening material. In some cases, the lines show evidence of high ionization states, suggesting they originate much closer to the quasar itself. Another possibility is that these peculiar spectral features are the result of relativistic beaming or Doppler shifting in unusual geometries. If a quasar's jet or accretion disk is oriented at just the right angle, it could drastically alter the apparent light profile. Add to this the effects of gravitational lensing, where the light of a quasar is bent and magnified by massive foreground galaxies, and the observed spectrum could become a warped version of the original signal. But these explanations, while plausible in isolated cases, fall short of explaining the broader pattern. There seems to be something intrinsic about these particular quasars that defies classification. And this is where the theories start to push the boundaries of contemporary astrophysics. Some researchers have proposed that inverted spectra might be the result of highly magnetized environments near the black hole, regions where the normal rules of atomic emission and absorption begin to break down. In such environments, known as magnetospheres, electrons spiral along magnetic field lines, emitting polarized radiation in complex patterns. If these regions are dense and chaotic enough, the light they produce could become filtered or reprocessed in ways that mimic inverted spectra. This would imply that the magnetic fields near some quasars are far stronger and more structured than previously believed. Others have gone even further, suggesting that inverted spectra could be a signature of exotic matter or even new particle interactions. If dark matter or some unknown field is interacting with radiation near the quasar, it could fundamentally alter the spectral signature before the light escapes. This idea, while speculative, opens the door to entirely new physics, perhaps even bridging the gap between quantum mechanics and general relativity. Even more intriguing is the idea that inverted spectra might not just be an observational artifact or a localized quasar feature, but a sign of evolutionary phases in galactic nuclei. Some models suggest that quasars undergo cycles of activity, periods of intense accretion followed by quieter phases, and possibly even states where the geometry or composition of the accretion disk shifts drastically. During these transitional phases, the energy output and emission mechanisms might behave in unpredictable ways, temporarily producing spectra that look inverted compared to the norm. Astronomers have also started to consider time domain effects. If the light we observe from a quasar is a mix of emissions from different epochs, because of gravitational lensing delays or scattering across large-scale structures, it might cause us to see an incoherent spectrum. In this case, one part of the light might represent a flaring period rich in emission lines, while another part reflects a dimmer phase dominated by absorption. The resulting composite would appear inverted or corrupted from our perspective. To add another layer of complexity, there's the issue of redshift. Quasars are among the most distant objects we can observe, and their light is stretched to longer wavelengths by the expansion of the universe. This redshifting affects how we interpret their spectra, and in high redshift quasars, the ultraviolet lines are moved into the optical or infrared range. If our instruments or models don't correctly account for this, what we interpret as an inverted spectrum might be a misidentified or misaligned redshifted feature. But even after correcting for redshift with the most advanced models and instruments, the anomalies persist. So, what does this all mean? It suggests we may be missing something fundamental about quasars, something essential about how light is generated and transmitted from these galactic cores. Inverted spectra could be a symptom of processes we've only begun to understand. Perhaps they indicate new mechanisms of radiative transfer, or hint at interactions between dark energy and matter near the event horizon. Maybe they're telling us that black holes aren't entirely black, or that the structure of spacetime around them isn't as smooth as Einstein imagined. The story of inverted spectra is far from over. With each new observation, astronomers peel back another layer of this cosmic mystery. Upcoming observatories like the James Webb Space Telescope and the Extremely Large Telescope will offer unprecedented resolution and sensitivity, potentially revealing faint spectral features or uncovering new classes of quasars with similarly bizarre properties. Meanwhile, data from older surveys like the Sloan Digital Sky Survey continue to be mined for overlooked anomalies, each one a possible key to unlocking a deeper understanding of the universe. And as we push deeper into this rabbit hole, one truth becomes increasingly clear: the cosmos is not just stranger than we imagined. It's stranger than we can imagine. Inverted spectra in quasars are not a glitch in the system. They are a message, an encrypted signal embedded in the starlight, waiting for us to decode it. These are not flukes, not data artifacts, and certainly not all explainable by instrumental noise or observational bias. The consistency and pattern of these spectral anomalies across independent observations and observatories point to a genuine astrophysical process, one that may be revealing hidden layers of quasar structure or even an entirely new class of luminous, high-energy objects. The scientific community has responded with a mixture of skepticism, curiosity, and cautious excitement. After all, it's not every day that the fingerprints of the universe rearrange themselves on our cosmic canvases. One of the first clues in attempting to decode inverted spectra lies in the idea of orientation and obscuration. In the Standard Model of Active Galactic Nuclei (AGN), of which quasars are the most luminous examples, much of what we see depends on our angle of view. A massive torus of gas and dust often surrounds the accretion disk and central black hole, and depending on how this torus is aligned with our line of sight, different parts of the structure can be obscured or revealed. This is the foundation of the so-called unified model of AGN, which suggests that quasars, Seyfert galaxies, and blazars are fundamentally the same phenomenon seen from different angles. If the torus or another dense region of gas sits directly between us and the central engine of a quasar, it can absorb or scatter certain wavelengths of light, leading to dramatic changes in the observed spectrum. But even with this understanding, the inversion of emission and absorption lines remains difficult to explain. In some of these quasars, the absorption is not only present, it mimics the very positions and strengths of expected emission lines. In essence, it appears as though the quasar is unemitting light in precisely the regions where it should be brightest. This is not easily accounted for by mere geometry. Another theory posits that we may be seeing the effects of intervening clouds of gas, perhaps in the host galaxy, or along the path to Earth, absorbing light at exactly the right frequencies to create a mirror image spectrum. This explanation aligns with phenomena such as broad absorption line (BL) quasars, where powerful winds driven by the central black hole eject material at near relativistic speeds. These winds can create blue-shifted absorption lines by absorbing light from the quasar before it escapes into space. However, the inverted spectra observed in some quasars don't match the usual profiles of BL quasars. The absorption features in balls are typically broad and asymmetrical, often with characteristic troughs and steep drop-offs in intensity. In contrast, the inverted lines in these peculiar quasars often appear sharp, symmetrical, and strangely precise, almost too perfect to be random intervening absorption. This leads to an even deeper mystery. Are we seeing light that has been processed in some unknown way? Light, as it travels through space, can interact with matter in complex and often subtle ways. It can scatter, reflect, refract, diffract, polarize, and undergo gravitational lensing. In extremely energetic environments near black holes, it can also be redshifted by gravity, distorted by frame-dragging effects, or even entangled in quantum-scale interactions that remain poorly understood. One provocative idea suggests that the inverted spectrum may be caused by a combination of these processes, a sort of layered optical illusion created by extreme gravity and relativistic effects. Some theorists have gone further, suggesting that we may be witnessing evidence of exotic particles or dark matter interactions in the vicinity of these quasars. If unknown particles are present near the quasar core, or if dark matter is somehow influencing the radiative processes, it could lead to unexpected spectral behaviors. This is, admittedly, speculative. But given how little we truly understand about dark matter, it remains a tantalizing possibility. What if, in some rare and extreme environments, dark matter does not merely sit passively in galactic halos but actively shapes how light is emitted and absorbed? Yet another possibility is rooted not in the quasar itself, but in the nature of space-time. The light from these distant quasars has traveled across billions of light-years, through expanding space, over cosmic voids and across intergalactic filaments. Along the way, it may have passed through gravitational lenses, massive galaxies or clusters that warp and bend the path of light. Normally, this gravitational lensing magnifies and distorts distant objects, allowing us to see farther into the universe than ever before. But under certain conditions, could lensing effects invert spectral features? Could multiple lensing events, overlapping in bizarre and unanticipated ways, cause absorption to masquerade as emission? While this scenario is theoretically possible, the conditions required would be extraordinarily rare and complex. Multiple alignments, precise mass distributions, and finely tuned distances would be necessary to create an effect consistent with an inverted spectrum. And yet, the universe is vast. If something is possible, even once, it likely has happened somewhere out there. Despite these speculations, the field remains cautious. Astronomers are rigorous in testing new claims, particularly those that challenge existing paradigms. Data must be independently verified, instruments recalibrated, and confounding variables eliminated. Still, the inverted spectra continue to surface, not frequently, but consistently enough to demand attention. What's perhaps most unsettling is that these inverted spectra force us to confront the limits of our understanding. They are reminders that, for all our progress, the cosmos still holds secrets we can't decode with certainty. They challenge not only our technical models of light and matter but our philosophical assumptions about observation and reality itself. What if we've misunderstood the very mechanisms of energy distribution in extreme environments? What if the quasar isn't malfunctioning, but rather, our interpretation of its light is? This question leads into a deeper realm of inquiry, one that bridges observational astronomy, high-energy astrophysics, quantum field theory, and even the philosophy of science. And as we explore this strange frontier, we are compelled to reevaluate what it means to see something in the universe. The notion of seeing something in the universe is far more complex than just interpreting light that arrives at our telescopes. It brings us face to face with the limitations of our observational tools and our understanding of the very fabric of reality. When we observe a quasar, or any cosmic phenomenon, we are not simply receiving light in its purest form. Instead, we are interpreting a signal that has been altered by the conditions through which it has traveled. The distance, gravitational forces, interstellar medium, and even the quantum nature of space-time itself, all of these factors influence the light we see. So, what if the inverted spectra observed in quasars are more than just an anomaly? What if they are a clue to a deeper layer of reality, one where our current theories about light, matter, and energy are not entirely correct? It's possible that these spectra represent a new, previously unconsidered aspect of the cosmos. Perhaps the light emitted by quasars is subject to interactions we've not yet accounted for, interactions that alter its properties in ways we still can't fully understand. In this context, the idea of exotic matter or dark energy affecting quasar spectra becomes even more compelling. We know that dark matter and dark energy make up a large portion of the universe's total energy budget, yet their exact nature remains one of the greatest mysteries in physics. If dark matter, for example, is composed of particles that interact weakly with normal matter, could they be influencing the propagation of light in these distant quasars in subtle ways? Could dark energy, with its influence on the expansion of the universe, be altering the light we observe? On the other hand, there's the possibility that the inversion of spectra is a manifestation of yet-to-be-understood physics occurring near the event horizons of supermassive black holes. In these environments, the laws of physics as we know them break down in bizarre and unexpected ways. The strong gravitational fields near black holes can bend, stretch, and warp spacetime itself. Light emitted from material near the event horizon would undergo extreme redshifting, and possibly blue shifting in other regions, depending on the relative motion of the emitting material and the observer's position. Could these relativistic effects create the inverted spectral features? Perhaps there is a subtle interplay between accretion disk dynamics, black hole spin, and the observer's perspective that is yet to be uncovered. Another intriguing possibility is related to the concept of gravitational time dilation. As light climbs out of a gravitational well, its frequency is stretched, which we observe as a redshift. However, if this process occurs differently for different regions of a quasar's accretion disk, the result might be a spectral inversion. If the material near the black hole is emitting light at one frequency, but we observe it from an angle where the light undergoes different amounts of gravitational distortion, we could see an inversion in the spectrum, emission lines appearing where absorption lines should be, and vice versa. Additionally, could these inverted spectra be a byproduct of the intricate relationship between matter and antimatter in these extreme environments? While antimatter is typically rare in the observable universe, it might exist in greater quantities in the vicinity of quasars, where the conditions are conducive to high-energy particle interactions. The annihilation of antimatter could result in unique electromagnetic signatures, including spectral features that are inverted from what we expect. If antimatter is present near a quasar's central black hole, could it be responsible for distorting the spectrum in this way? The detection of these anomalies would certainly require a re-evaluation of our models of quasar physics. Another potential explanation revolves around the role of high-energy jets and outflows. Many quasars are known to have powerful relativistic jets, which shoot out along the rotational axis of the black hole. These jets are composed of highly energetic particles, including electrons and protons, that are accelerated to near the speed of light. When these particles interact with the surrounding magnetic fields, they emit electromagnetic radiation across a broad spectrum, from radio waves to gamma rays. The interaction of these jets with the surrounding gas could potentially create unusual spectral features. If the jets are interacting with the accretion disk or the surrounding interstellar medium in such a way that certain wavelengths are absorbed or emitted in unexpected patterns, this might explain some of the inverted spectral observations. But perhaps the most mind-boggling possibility is that the inverted spectra are not due to any known astrophysical process, but represent a new form of cosmic phenomena altogether, something entirely outside the realm of our current models. This could be the discovery of a new class of objects or phenomena that fundamentally change our understanding of the universe. If we are indeed seeing the aftermath of exotic matter, dark energy, or unknown quantum interactions, then we might be standing on the precipice of a new frontier in astrophysics. The implications of such a discovery would ripple through nearly every field of physics, from quantum mechanics to general relativity to the study of dark matter and dark energy. If inverted spectra are truly revealing a new type of object or process, then we must reconsider what it means to classify astronomical objects. For decades, we have categorized quasars based on their luminosity, spectra, and energy output. But what if this classification is insufficient? What if these inverted spectra are pointing us toward a new class of quasars or black hole systems, ones that behave in radically different ways from the quasars we currently understand? The discovery of this new class could be as transformative as the discovery of pulsars or black holes themselves, forcing astronomers to rethink entire areas of their models. So, the question remains, what exactly are we seeing when we observe inverted spectra in quasars? The answer is likely far more complicated than a simple observational error or a small variation in quasar behavior. The data we are collecting suggests that there is something far more profound going on, something that could challenge the very foundations of modern astrophysics. And as our observational tools improve and our understanding of the universe deepens, we will no doubt continue to refine our models and hypotheses, hopefully unlocking the mysteries of these inverted spectra once and for all. The study of inverted spectra in quasars may very well represent one of the most exciting frontiers in modern astronomy. Each new observation could bring us closer to unraveling the secrets of the universe, secrets that have been hidden in plain sight, encoded in the very light from the most distant and powerful objects in the cosmos. As we move forward, one thing is certain: the universe has much more to reveal, and the quest to understand these spectral anomalies will undoubtedly lead to new discoveries that will reshape our understanding of the cosmos. The allure of quasars, particularly the enigmatic inverted spectra they exhibit, is undeniable. They pull at the heart of astrophysical curiosity, urging us to probe deeper into the fundamental workings of the universe. As we continue our exploration, we must also consider how these phenomena might fit into broader cosmic events, offering us glimpses of processes that transcend typical cosmic understanding. As more advanced telescopes come online, especially those that observe in the infrared and radio wavelengths, we will be able to obtain even more detailed data on quasars and their spectra. With the advent of instruments like the James Webb Space Telescope, JWST, and the upcoming next-generation observatories, the ability to probe deeper into the universe's most distant corners will provide crucial insights. These tools will allow us to analyze the fine details of quasar light that we could only dream of studying in the past. The process of obtaining and analyzing light from distant quasars is akin to being a detective piecing together an ancient puzzle. The inverted spectra we observe are like cryptic messages left by the quasars themselves, waiting to be decoded. To better understand these messages, we must consider how the light we observe has traveled across the vast distances of space and time, passing through various cosmic environments before reaching us. The light may be altered by gravitational lensing, absorption by intergalactic dust, or even interactions with unknown quantum phenomena. One of the primary reasons these inverted spectra are so puzzling is the lack of a clear model that explains them within the framework of our current understanding of physics. Astronomers and physicists are accustomed to understanding spectral lines based on the idea of absorption and emission lines, light that is absorbed or emitted by elements in a star's atmosphere or an accretion disk. This provides a clear picture of the chemical composition and temperature of objects in the universe. However, the inversion of these lines suggests that there is something at play that is not just altering the light but perhaps changing the fundamental behavior of photons themselves. Gravitational lensing, a phenomenon in which light from a distant object is bent by the gravitational field of an intervening object, like a galaxy, could distort the observed spectra. This effect is well understood and has been used to study galaxies and quasars far beyond the reach of traditional telescopes. However, gravitational lensing alone does not fully account for the inverted spectral features we observe. Instead, it's likely that multiple factors are combining to produce these unusual observations. As we explore the concept of gravitational time dilation, another possibility arises. Time dilation occurs in regions of extreme gravity, where time itself slows down relative to less massive regions of space. This means that light emitted from regions near a black hole, for example, could be significantly delayed compared to light emitted further away. This effect might cause the observed spectra to shift in ways we would not expect under normal conditions, potentially leading to the inverted lines we see. However, to fully understand how this could occur, we would need a more refined model of black hole accretion disks and the relativistic jets emanating from these regions. At the same time, we can't ignore the role of magnetic fields in these extreme environments. Magnetic fields are known to play a crucial role in the behavior of plasma around black holes and other compact objects. When highly energetic particles in these plasma regions interact with magnetic fields, they can emit radiation across a wide range of wavelengths. The exact behavior of these particles and the role of magnetic fields in shaping the light emitted by quasars is still an area of active research. It's possible that the inverted spectra we observe are a result of the interplay between these magnetic fields and the motion of particles in the accretion disk. The magnetic field could be distorting the emission lines in ways that are not yet fully understood. Another intriguing aspect of quasar spectra is the possibility of an intrinsic property of the quasars themselves, a feature that is not simply the result of interactions with their environment, but rather something inherent to the quasar's physical structure or energy production mechanisms. Could quasars possess a unique spectral signature that is part of their fundamental nature, something that sets them apart from other cosmic objects? This is an area that requires more investigation, and as we continue to observe quasars in more detail, we may begin to uncover patterns that suggest there is something fundamentally different about these objects compared to other types of galaxies or black holes. One additional factor that could be influencing quasar spectra is the density of the surrounding intergalactic medium. This vast region of space is not empty. Rather, it contains a low-density plasma that can interact with light passing through it. This intergalactic medium, composed of hydrogen and other elements in ionized states, could be absorbing or scattering light from the quasar in ways that alter its spectral features. The exact nature of this interaction is still a topic of debate among cosmologists and astronomers, but it's possible that the interplay between quasar light and the intergalactic medium is contributing to the inverted spectra observed. Furthermore, it's important to consider the potential role of cosmic inflation in the behavior of quasar light. Cosmic inflation, the rapid expansion of the universe that occurred during the first few moments after the Big Bang, may have set the stage for the large-scale structure of the universe we observe today. This early inflationary period could have had lasting effects on the distribution of matter, energy, and even light across the cosmos. If quasars are relics from the early universe, then their spectra could be influenced by the imprint of inflationary processes that we have yet to fully understand. The subtle effects of inflation on light could be revealing themselves in the form of inverted spectral lines. The concept of multiverse theory cannot be completely ruled out in discussions of phenomena like inverted spectra. While highly speculative, the idea that our universe might be just one of many in a vast multiverse opens up the possibility that the physical laws in distant regions of the multiverse could differ from our own. If the laws of physics vary across different universes, then we might expect to observe anomalies, like inverted spectra, when light from distant quasars interacts with these alternate physical conditions. Though this idea remains highly theoretical, the concept of a multiverse offers a tantalizing framework for understanding some of the most perplexing phenomena in modern cosmology. The study of inverted spectra in quasars is an ongoing mystery that continues to captivate the minds of astronomers and physicists alike. These anomalies may point to hidden layers of reality, revealing new aspects of the universe that we are only beginning to comprehend. Whether caused by gravitational time dilation, the interplay of magnetic fields, the nature of the intergalactic medium, or even the imprint of cosmic inflation, the inverted spectra offer a glimpse into the unknown. As our observational techniques continue to improve and our theoretical models evolve, we are bound to uncover new insights that will reshape our understanding of quasars and the universe itself. The answers may lie in the most unexpected places, but one thing is clear: the journey of discovery is far from over, and the universe still has much to reveal. The mystery of inverted spectra in quasars is only one piece of the cosmic puzzle. As we continue to study these distant objects, we are faced with a deeper understanding of the fundamental laws of physics, cosmology, and even the origins of the universe itself. With each new discovery, the picture becomes clearer, yet at the same time, more complex. The study of quasars, and specifically their spectral behavior, may eventually lead us to answers that are completely unexpected, pushing the boundaries of our knowledge in ways we can scarcely imagine. Looking forward, the quest for understanding these inverted spectra could open up entirely new fields of study in astrophysics. For instance, future research into the behavior of matter in extreme environments, such as the regions close to black holes and quasars, could yield new insights into how gravity, electromagnetism, and quantum mechanics interact under conditions far more extreme than anything we experience on Earth. This research may even help us understand phenomena like dark matter and dark energy, two of the most elusive components of the universe that remain largely unexplained. As we delve deeper into these complex topics, we must also consider the theoretical models that could help explain the inverted spectra. Current models rely heavily on established principles of astrophysics, such as general relativity and the standard model of particle physics, but these frameworks have their limitations. In particular, general relativity struggles to fully describe the quantum processes that are thought to occur near the event horizon of a black hole, where quasars are often found. This is where theories like quantum gravity and string theory come into play. By combining the principles of quantum mechanics with those of general relativity, these theories seek to describe how gravity behaves at extremely small scales that we can only begin to probe with the most sophisticated instruments. String theory, in particular, suggests that the universe is made up of tiny, vibrating strings, and that the properties of these strings could explain the fundamental forces of nature, including gravity. If these ideas hold true, they could provide a new way of understanding the phenomena we observe in quasars. For example, it might help explain the interaction between light and the extreme gravitational fields near black holes, shedding light on how the inverted spectra could form. The implications of such a discovery would be profound, potentially reshaping our entire understanding of the universe. Additionally, the study of quasars and their spectra is closely tied to our understanding of the evolution of the universe itself. Quasars are believed to be some of the earliest objects formed in the universe, created in the aftermath of the Big Bang. These powerful sources of light may offer a glimpse into the conditions that existed in the very early universe, potentially unlocking secrets about the formation of galaxies, stars, and black holes. By studying the spectra of quasars, we can learn about the chemical composition and physical properties of the gas and dust that filled the early universe, helping to piece together the story of how our universe came into being. One fascinating avenue of exploration is the connection between quasars and the supermassive black holes that lie at their centers. These black holes are thought to be millions to billions of times more massive than our Sun, and they are responsible for the immense energy that quasars emit. Understanding the dynamics of these supermassive black holes, and the environments in which they exist, is key to unlocking the mystery of inverted spectra. As we observe more quasars and improve our ability to measure their spectra, we may discover new insights into the relationship between these black holes and their surrounding environments. At the same time, the behavior of light in the presence of extreme gravitational fields, like those near black holes, may offer clues about the nature of spacetime itself. According to Einstein's theory of general relativity, massive objects warp the fabric of spacetime around them, causing light to follow curved paths. In the case of quasars, this warping could be influencing the way we observe their spectra. This means that the inverted spectra we observe could be a result of light traveling through regions of intense gravity, where time and space behave in ways that are difficult to predict. Another important aspect of studying quasars and their inverted spectra is the role that they play in the broader context of galaxy evolution. Quasars are often found at the centers of galaxies, and their immense energy output can have a profound impact on the surrounding environment. The energy emitted by a quasar can blow away surrounding gas and dust, preventing the formation of new stars. This process, known as feedback, is thought to play a crucial role in the evolution of galaxies. By studying quasars, we can gain a better understanding of how this feedback mechanism works and how it influences the formation and evolution of galaxies over time. One of the challenges in studying quasars, especially those with inverted spectra, is the vast distances that separate us from these objects. The light we observe from a quasar today was emitted billions of years ago, meaning that we are looking at a snapshot of the universe as it was in the distant past. This time lag presents a unique opportunity to study the universe's history, but it also makes it difficult to understand the current state of these objects. Future advancements in technology, particularly in the realm of observational instruments, will allow us to study quasars in even greater detail, providing new insights into their spectra and the phenomena that shape them. As we continue to unravel the mysteries of quasars and their inverted spectra, we must also remain open to the possibility that our current understanding of physics may not be sufficient to explain all the observations we are making. The universe is full of surprises, and the study of quasars could lead us to discoveries that challenge our most basic assumptions about the nature of reality. This is what makes the study of quasars so exciting. Each new discovery brings us closer to understanding the deepest secrets of the cosmos, while also reminding us that there is still much we have yet to learn. In the coming years, we can expect to see an explosion of new data and insights about quasars, especially as the next generation of telescopes comes online. These instruments will allow us to observe quasars with unprecedented clarity, revealing new details about their spectra, their behavior, and their role in the universe. By combining these observations with our growing understanding of astrophysical theories, we will be able to build a more complete picture of these extraordinary objects, and perhaps even unlock the answers to the many questions that remain. The study of inverted spectra in quasars is a journey that promises to reveal new frontiers in our understanding of the universe. With every discovery, we come closer to understanding the complex forces and phenomena that shape the cosmos, while also expanding our knowledge of the fundamental laws that govern reality. As we continue to explore these distant and mysterious objects, we will undoubtedly uncover new and unexpected insights that will redefine our understanding of the universe and our place within it. The mysteries of quasars, and the inverted spectra they exhibit, are just the beginning of a much larger cosmic story that is waiting to be told. The ongoing exploration of quasars, particularly those with inverted spectra, serves as a reminder that our understanding of the cosmos is constantly evolving. As our observational tools and theoretical models improve, new questions will arise, pushing us further into the unknown. This continuous journey of discovery holds the promise of revolutionizing our understanding of the universe at its most fundamental levels. One area that will likely see significant advancements is the study of quasar formation and their relationship to the supermassive black holes at their centers. Quasars are thought to form when gas and dust fall into a supermassive black hole, where they are heated to extreme temperatures, causing the release of intense radiation. This process is often referred to as accretion, and it is responsible for the immense luminosity of quasars. However, the exact mechanisms behind this process are still not fully understood, and the inverted spectra observed in some quasars could provide crucial clues about how accretion works in these extreme environments. The interplay between the black hole, the surrounding gas, and the light emitted by the quasar is a complex system that is still not entirely understood. The inverted spectra observed in some quasars may be an indication that something unusual is happening in the region surrounding the black hole. For example, it could be that the high-energy radiation from the quasar is interacting with the gas in ways that are not yet fully understood, causing the observed spectral inversion. Understanding this interaction could help scientists uncover new aspects of the accretion process, as well as shed light on the behavior of matter and energy in these extreme environments. Another intriguing possibility is that the inverted spectra could be the result of the gravitational lensing effect, where the light from the quasar is distorted by the gravitational field of a massive object, such as a galaxy or a cluster of galaxies, between the quasar and Earth. Gravitational lensing is a well-known phenomenon that can magnify and distort the light from distant objects, and it has been observed in many different contexts. However, the possibility that gravitational lensing could be responsible for the inverted spectra in quasars adds an additional layer of complexity to the study of these objects. If this theory is correct, it would mean that the inversion of the spectra is not due to the intrinsic properties of the quasar itself, but rather the result of the light's journey through space. To test this hypothesis, scientists would need to examine quasars that are known to be gravitationally lensed by other objects. By comparing the spectra of these lensed quasars with those of quasars that are not lensed, researchers could determine whether gravitational lensing is playing a role in the observed spectral inversion. This type of research could lead to new insights into the nature of gravitational lensing and its effects on the light from distant objects. As our understanding of quasars continues to evolve, so too does our understanding of the larger cosmic structure in which they reside. Quasars are not isolated objects. They are part of a much larger and more complex network of galaxies, black holes, and other celestial bodies that make up the universe. Understanding the role of quasars in this larger context is crucial for developing a more complete picture of the universe's evolution. For instance, quasars are thought to play a key role in the formation and growth of galaxies. Their intense radiation can heat up and blow away surrounding gas, preventing new stars from forming in the regions surrounding the quasar. This feedback mechanism can have a profound effect on the evolution of galaxies, and studying quasars may help us understand how galaxies grow and evolve over time. In recent years, researchers have also begun to study the connection between quasars and the large-scale structure of the universe. Quasars are thought to be located in the most distant regions of the cosmos, meaning that they can offer a glimpse into the early universe, shortly after the Big Bang. By studying the light from these distant objects, scientists can learn more about the conditions that existed in the early universe, including the formation of the first galaxies, stars, and black holes. This research has the potential to unlock new insights into the origins of the universe itself, providing clues about how the cosmos came into existence and how it has evolved over billions of years. One of the most exciting developments in the study of quasars is the advent of next-generation telescopes, which promise to revolutionize our understanding of these objects. Instruments like the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescope, ELT, will allow scientists to observe quasars in greater detail than ever before. These telescopes are equipped with advanced technologies that will enable researchers to study the spectra of quasars with unprecedented precision, potentially revealing new details about their behavior, composition, and the mechanisms that drive their intense radiation. With these new tools at our disposal, we are on the cusp of making groundbreaking discoveries that could reshape our understanding of the universe. For instance, the JWST is capable of observing the infrared portion of the spectrum, which will allow scientists to study the dust and gas surrounding quasars in greater detail. This could provide new insights into the processes that occur in the regions near supermassive black holes, as well as help us understand how quasars interact with their surroundings. Similarly, the ELT, with its enormous primary mirror, will allow for incredibly detailed observations of distant quasars, providing a clearer picture of their spectra and the physical processes occurring in their immediate vicinity. These observations could help clarify the role of quasars in the formation of galaxies and shed light on the complex relationships between black holes, quasars, and the larger cosmic structure. The study of inverted spectra in quasars is just one facet of this broader quest for knowledge. As we continue to explore the mysteries of these enigmatic objects, we will undoubtedly uncover new insights that challenge our understanding of the universe. These discoveries may not only help us explain the phenomena we observe in quasars, but also lead to broader breakthroughs in our understanding of the laws of physics, the nature of spacetime, and the evolution of the cosmos itself. The study of quasars and their inverted spectra is about more than just understanding one specific phenomenon. It is about pushing the boundaries of human knowledge and expanding our understanding of the universe. With each new discovery, we come closer to answering some of the most fundamental questions about the nature of reality, and we are reminded that the universe is far more complex and mysterious than we could ever have imagined. As we continue to look to the stars, we are not only exploring the distant reaches of space, but also venturing into the unknown depths of our own understanding. As the study of quasars and their inverted spectra unfolds, it becomes clear that these cosmic phenomena are not just objects of fascination for astronomers. They are windows into the very workings of the universe itself. Their study provides clues not only about the distant past of the universe but also about the physical laws that govern everything from the behavior of light to the formation of the largest structures in the cosmos. Every new piece of data that we gather from these distant objects helps us build a clearer picture of the fundamental forces and processes at play in the universe. The inverted spectra observed in certain quasars present an intriguing anomaly, challenging our traditional models of astrophysics. This anomaly has inspired a wealth of research, all of which is pushing the boundaries of how we understand light, matter, and space. As we delve deeper into these enigmatic objects, we discover that quasars may hold the key to answering some of the most profound questions in modern physics. One such question is the true nature of the supermassive black holes at the centers of these quasars. While it is widely accepted that quasars are powered by accretion disks surrounding supermassive black holes, the exact mechanisms of how this process unfolds are still not fully understood. The presence of inverted spectra in certain quasars adds a layer of complexity to this question. Could the inversion be a clue to the inner workings of the accretion disk? Could it be indicative of new physical phenomena occurring in the extreme environments near black holes that we have yet to observe? Recent simulations and theoretical models have begun to shed light on these possibilities. The idea that inverted spectra could be caused by unusual physical conditions in the accretion disk itself is one area of active research. These disks are made up of gas and dust swirling around the black hole at incredibly high speeds. As this material gets pulled in, it becomes intensely heated, emitting radiation across the entire electromagnetic spectrum. However, certain physical effects could distort this radiation in ways that result in the observed inverted spectra. For example, the effects of intense magnetic fields, relativistic jets, or even the gravitational pull of the black hole could all contribute to this unusual behavior. Magnetic fields are of particular interest in the study of quasars. In some models, the presence of strong magnetic fields within the accretion disk could be responsible for altering the emission of light from the quasar. These magnetic fields could trap or bend the radiation emitted by the hot gas, resulting in the inverted spectral features we observe. Additionally, these magnetic fields could play a role in the formation of relativistic jets, streams of charged particles that are ejected from the poles of the black hole at nearly the speed of light. These jets can interact with the surrounding material, further complicating the spectral signatures of quasars. The interplay between magnetic fields, accretion disks, and relativistic jets is still poorly understood, but the study of inverted spectra could be key to unraveling this complex web of interactions. Another possible explanation for the inverted spectra lies in the gravitational effects of the black hole itself. The intense gravity near the event horizon of a black hole warps the fabric of spacetime, causing a phenomenon known as gravitational redshift. As light from the quasar travels through this warped spacetime, its wavelength is stretched, causing it to shift toward the red end of the spectrum. In certain situations, this effect could result in the inversion of spectral lines, depending on the precise geometry of the black hole's surroundings and the orientation of the accretion disk. This theory suggests that the inversion is not the result of an unusual emission process, but rather the effect of the black hole's powerful gravitational field on the emitted radiation. Gravitational redshift is a well-established effect, but its contribution to the observed spectra of quasars is still a topic of debate. Some researchers believe that it is the primary cause of spectral inversion, while others argue that other factors, such as magnetic fields or relativistic effects, are more significant. To resolve this debate, more detailed observations and simulations are needed to determine the exact contribution of gravitational redshift to the spectral features of quasars. This research could have far-reaching implications for our understanding of black holes and their influence on the surrounding space. As we explore these ideas, it is important to remember that quasars are not isolated objects. They are part of the broader cosmic landscape, interacting with the galaxies in which they reside and influencing the evolution of the universe itself. Quasars are thought to play a crucial role in the formation and growth of galaxies. Their immense energy output can have a profound impact on their surroundings, driving the processes of star formation and galaxy evolution. In some cases, the radiation from a quasar can even blow away the gas and dust in its host galaxy, effectively quenching further star formation and preventing the galaxy from continuing to grow. This feedback mechanism is a key aspect of galaxy formation theory, and studying quasars provides valuable insights into how galaxies evolve over time. Moreover, the study of quasars is intricately tied to the study of large-scale cosmic structures. Because quasars are some of the most distant objects in the universe, they provide a unique opportunity to probe the early stages of the universe's evolution. Their light travels across vast distances, taking billions of years to reach us, and in doing so, it passes through the various structures that formed in the early universe. By studying the light from quasars, astronomers can learn about the conditions in the universe shortly after the Big Bang, providing a glimpse into the infancy of the cosmos. For example, the light from quasars can reveal the properties of the intergalactic medium, the gas and dust that fills the space between galaxies. This medium is thought to have played a crucial role in the formation of the first galaxies and stars. By analyzing the absorption lines in the spectra of quasars, scientists can learn about the density, temperature, and composition of the gas in the early universe. This research is helping to shape our understanding of the processes that led to the formation of the first structures in the universe. Additionally, the study of quasars and their inverted spectra can shed light on the properties of dark matter and dark energy, two of the most mysterious and poorly understood components of the universe. Dark matter is believed to make up the majority of the mass in the universe, yet it does not interact with light or other forms of electromagnetic radiation, making it extremely difficult to detect. However, quasars may provide indirect evidence of dark matter through the way their light is affected by gravitational lensing. By studying how quasars are distorted by the gravitational influence of dark matter in galaxy clusters, scientists can learn more about the properties of this elusive substance. Similarly, dark energy, the mysterious force driving the accelerated expansion of the universe, may also be detectable through the study of quasars. Quasars are thought to be sensitive to changes in the geometry of spacetime, which could be influenced by the presence of dark energy. By examining the spectra of distant quasars, researchers may be able to detect subtle effects caused by the expansion of the universe and gain insights into the nature of dark energy itself. In the coming years, the study of quasars will continue to play a central role in cosmology. With the advent of new observational tools and technologies, we are poised to make groundbreaking discoveries that will deepen our understanding of the universe and its fundamental components. The mysteries surrounding inverted spectra in quasars are just the beginning, and as we continue to study these fascinating objects, we are likely to uncover even more surprising and transformative insights into the nature of the cosmos. As we move forward, the quest to understand quasars, their inverted spectra, and their place in the universe will continue to push the boundaries of human knowledge. Every discovery brings us one step closer to unraveling the deepest secrets of the cosmos, and with each step, we inch closer to answering some of the most profound questions about the universe, space, and time. As the pursuit of knowledge about quasars and their inverted spectra progresses, the implications for both astrophysics and cosmology become ever more significant. The findings from these studies don't just enhance our understanding of distant objects, they reshape the way we think about the universe, the fundamental forces that govern it, and the very nature of spacetime itself. Inverted spectra, which continue to perplex astronomers and physicists alike, could be the key to unraveling some of the most profound mysteries of the cosmos. One of the most exciting aspects of studying quasars is the way these distant objects illuminate the extremes of physics. The incredible conditions found in and around quasars allow us to test our theories in realms that are otherwise inaccessible. The radiation emitted by quasars, particularly in the form of their inverted spectra, offers a glimpse into the behavior of matter and energy in environments that are radically different from anything we can replicate here on Earth. This makes them invaluable laboratories for testing the limits of known physics. The black holes at the centers of quasars, often billions of times more massive than our Sun, are places where gravity becomes so intense that it warps the fabric of space-time. The closer you get to the black hole, the stronger the gravitational pull becomes, bending light and distorting everything around it. The strange effects of this intense gravitational field may be behind the phenomena we see in the inverted spectra. For example, the accretion disk surrounding the black hole, a swirling mass of gas and dust, may undergo extreme relativistic effects that alter the light emitted. This could lead to the observed spectral inversion, where certain wavelengths of light are intensified while others are diminished. As we probe deeper into the dynamics of these accretion disks, we encounter another intriguing aspect of quasar physics: the relationship between matter and radiation in extreme gravitational fields. In some quasars, the inverted spectra may be caused by the behavior of radiation as it interacts with the surrounding material. As the matter in the accretion disk is pulled in toward the black hole, it heats up to millions of degrees, emitting vast amounts of energy across the entire electromagnetic spectrum. However, because of the extreme conditions, the radiation emitted from different parts of the disk might travel along different paths, subject to varying amounts of gravitational bending. This could lead to the observed spectral inversions, as different wavelengths of light from various regions of the disk are altered differently as they move through the gravitational well of the black hole. Additionally, the relativistic jets that are often associated with quasars add another layer of complexity to this puzzle. These jets, which shoot out from the poles of the black hole at nearly the speed of light, carry with them enormous amounts of energy. As they move through space, they interact with surrounding gas and dust, further modifying the emission spectra of the quasar. These interactions might also contribute to the inverted spectra observed in some quasars. The jets themselves could emit radiation that distorts the light from the accretion disk, producing the characteristic spectral inversion. Another possibility is that the inverted spectra are caused by the way light interacts with the gas surrounding the black hole. This gas is not static. It's constantly moving and can have significant effects on the radiation emitted by the accretion disk. For instance, if the gas is moving toward us at a significant fraction of the speed of light, it could shift the emitted light into shorter wavelengths, a phenomenon known as blue shift. Conversely, if the gas is moving away from us, it could cause the light to shift toward longer wavelengths, or redshift. In some cases, the combined effects of these shifts might result in a spectrum that appears inverted, with certain wavelengths appearing more intense than others in a way that defies our usual expectations. This leads to the broader question of how our understanding of quasars, and the physical processes behind their spectra, can be used to test fundamental theories in physics. For instance, the inverted spectra observed in quasars could be related to the so-called gravitational lensing effect, where the intense gravity of a black hole bends light coming from behind it. This effect has been observed in other parts of the universe, such as with galaxies and clusters of galaxies, but quasars provide a much more detailed and accessible way to study this phenomenon. The study of inverted spectra could thus offer new insights into how light behaves in curved spacetime and provide additional confirmation of general relativity, one of the cornerstones of modern physics. On a more theoretical level, the continued investigation of quasars with inverted spectra could shed light on the nature of the universe itself. As mentioned earlier, quasars are some of the most distant objects we can observe, and studying their light gives us a direct window into the early universe. The study of their spectra, including any unusual inversions, could help answer questions about the composition of the early universe, the formation of galaxies, and the processes that led to the creation of the first stars. The data gathered from these studies could even reveal new physics that could change the way we view the very fabric of reality. Moreover, the study of quasars and their spectra also ties into the larger quest to understand the ultimate fate of the universe. Quasars are often associated with some of the most energetic and extreme processes in the cosmos. Understanding how these objects work, and how their spectra can be altered, might help us answer questions about the future of our own universe. Could quasars help us understand how galaxies evolve over time? Could their energy outputs offer clues about the rate of expansion of the universe, and how this expansion will continue to evolve? The answers to these questions may lie in the inverted spectra of quasars, waiting to be discovered. The role of quasars in the ongoing search for new physics extends far beyond the realm of traditional astrophysics. Quasars could also be crucial in the study of dark matter and dark energy, two of the most profound mysteries in modern science. As we've discussed, quasars interact with the fabric of spacetime in ways that could reveal the presence of dark matter, and the study of their spectra may allow us to indirectly detect the influence of this mysterious substance. Similarly, the way quasars behave at extreme distances could provide new insights into the nature of dark energy and its impact on the expansion of the universe. These studies may hold the key to unlocking the ultimate nature of the forces that govern the cosmos. In the coming years, as our observational tools become more sophisticated, we are likely to gain an even deeper understanding of quasars and their inverted spectra. Instruments like the James Webb Space Telescope, which is set to revolutionize our ability to study the universe in unprecedented detail, will undoubtedly play a critical role in advancing our knowledge of these enigmatic objects. With its ability to observe the universe in infrared wavelengths, Webb will allow scientists to probe the interiors of quasars and the regions surrounding black holes with unmatched precision. The insights gained from this next generation of space telescopes will no doubt be essential for unraveling the mysteries of quasars and their role in the broader cosmos. Quasars, with their powerful emissions and extreme conditions, remain some of the most fascinating objects in the universe. The inverted spectra they display only add to the intrigue, offering a unique challenge to our understanding of light, gravity, and the nature of space-time. As we continue to observe and study these remarkable objects, we are bound to uncover new layers of mystery, and in doing so, continue to push the boundaries of human knowledge. By delving into the peculiarities of quasar spectra, including the enigma of the inverted spectrum, we are not only investigating distant, far-off objects. We are investigating the fundamental nature of the universe itself, its origins, and its fate. Each discovery, each breakthrough, brings us one step closer to understanding the deeper truths that govern everything, from the formation of stars to the very forces that shape reality. And as our comprehension of these extraordinary cosmic phenomena grows, so too does our understanding of the universe as a whole. Every quasar, every twist in its spectrum, is a clue, a piece of the cosmic puzzle we are all trying to solve. And as the field of quasar research advances, so too will our capacity to comprehend the true nature of the universe and our place within it. As we continue to probe deeper into the heart of quasars and their inverted spectra, it's clear that each new observation brings with it a fresh layer of complexity. The more we learn about quasars, the more we realize how little we actually know about the forces at play in these distant, powerful objects. The study of quasars challenges our current understanding of physics, cosmology, and the universe itself, forcing us to reconsider long-held assumptions and explore new theoretical frameworks. One of the key questions that arises in the study of quasars is the issue of scale. Quasars are not just distant objects, they are also incredibly massive, with black holes at their centers often weighing millions, if not billions, of times more than the mass of our Sun. This immense mass results in an extraordinary gravitational field that influences everything in its vicinity, bending light and distorting the fabric of spacetime. The spectra of quasars, particularly those with inverted features, provide direct evidence of this intense gravitational influence. But the real challenge lies in deciphering how this gravitational pull affects the radiation we observe from these objects. The phenomenon of gravitational redshift, for instance, offers a window into understanding how light behaves near the event horizon of a black hole. In general relativity, light emitted from a source near a massive object will lose energy as it climbs out of the gravitational well, causing a shift toward longer wavelengths, what we call redshift. In quasars, however, the situation is more complex. While some regions of the accretion disk may be subject to gravitational redshift, other parts may experience blue shift, where light is compressed into shorter wavelengths as it is pulled toward the black hole. This dichotomy of redshift and blue shift could potentially explain the spectral inversions we observe in certain quasars. In addition to gravitational redshift and blue shift, other relativistic effects may contribute to the inverted spectra. For example, relativistic beaming could be at play in the powerful jets that quasars emit. These jets, traveling at speeds close to the speed of light, can cause a dramatic shift in the observed intensity of radiation depending on the angle at which we view them. If we are looking directly along the axis of the jet, we might observe a boost in the intensity of certain wavelengths, while other wavelengths may be diminished due to the Doppler effect. This could result in a spectrum that appears inverted, with some emission lines stronger than they would be in a stationary, non-relativistic source. The role of magnetic fields in quasars is another important factor to consider. Magnetic fields in and around the accretion disk and the relativistic jets are likely to play a significant role in shaping the spectra of quasars. These fields can accelerate charged particles to nearly the speed of light, causing them to emit synchrotron radiation, high-energy radiation that can dominate the emission spectrum of a quasar. The interplay between these magnetic fields and the material in the accretion disk may alter the emission of radiation in unexpected ways, potentially contributing to the observed spectral inversions. Magnetic fields also have a direct impact on the dynamics of the jets themselves. These jets are often tightly collimated and can stretch out over vast distances, emitting radiation across a broad range of wavelengths. As the jets interact with the surrounding intergalactic medium, they can produce complex emission lines that are influenced by the motion of the material and the magnetic fields within them. This interaction could lead to the creation of inverted spectra in certain cases, especially when the jet is moving at relativistic speeds or is oriented in such a way that its emission is directed toward Earth. But the story doesn't end with these known phenomena. Quasars continue to push the boundaries of what we understand about the universe, and the inverted spectra we observe may hold clues to new, unexpected processes that have yet to be discovered. As observational technology continues to improve, we will likely gain new insights into the precise mechanisms behind these spectral anomalies. The upcoming generation of space telescopes, such as the James Webb Space Telescope, is set to reveal more about quasars and their surroundings than ever before. These instruments will allow us to observe quasars in unprecedented detail, opening new windows into their complex structures and behaviors. The detailed study of quasar spectra is also crucial for our broader understanding of the evolution of galaxies and supermassive black holes. Quasars are thought to be in a transitional phase in the life of galaxies, often representing an active period when the supermassive black hole at the center of a galaxy is rapidly accreting material. This process, known as the quasar phase, is thought to occur when a galaxy's central black hole is actively growing by pulling in gas, dust, and other material. Understanding the conditions under which quasars emit their unique spectra, particularly inverted spectra, could help us learn more about the formation and evolution of galaxies and black holes over cosmic time. Interestingly, some scientists have proposed that the presence of inverted spectra in quasars could be linked to the idea of cosmic evolution itself. In the early universe, quasars were much more common than they are today. The gas and dust that fed these early black holes likely played a significant role in the processes that shaped the first galaxies. By studying the spectra of distant quasars, we gain insight into the state of the universe at various points in its evolution. The presence of inverted spectra in certain quasars could therefore reveal information about the conditions that existed in the early universe, as well as the processes that led to the formation of galaxies, stars, and other cosmic structures. As we continue to study the inverted spectra of quasars, we are not only uncovering the mysteries of distant, massive objects, we are also building a more complete picture of the universe's history. From the birth of galaxies to the behavior of supermassive black holes, the study of quasars offers invaluable insights into the fundamental processes that have shaped the cosmos. And as technology advances, we can expect even more groundbreaking discoveries, with each new finding bringing us one step closer to understanding the deeper truths that govern the universe. The study of quasars and their inverted spectra is a prime example of how the pursuit of knowledge often leads to more questions than answers. Each new observation uncovers new layers of complexity, challenging us to rethink our models and refine our understanding of the universe. And as we continue to explore the cosmos, we must remain open to the possibility that there are still many more mysteries waiting to be uncovered, mysteries that could change the way we see the universe and our place in it. Quasars, with their incredible energy and enigmatic properties, remain one of the most captivating subjects in modern astronomy. The inverted spectra that some of these objects exhibit provide a unique glimpse into the complex interplay between matter, light, and gravity in the most extreme environments in the universe. While the exact mechanisms behind these spectra are still not fully understood, the ongoing study of quasars promises to yield new insights into some of the most fundamental questions in physics and cosmology. And as we continue to unravel these mysteries, we may find that the answers are even more astonishing than we could have imagined. As we continue to explore the depths of quasars and their inverted spectra, it becomes clear that these objects offer us not only a window into the most extreme corners of the universe but also an opportunity to test the limits of our scientific theories. Quasars, with their massive black holes, enormous energy outputs, and complex behaviors, provide a natural laboratory where the laws of physics are pushed to their very limits. The study of these enigmatic objects forces us to confront some of the most profound questions in astrophysics and cosmology. One of the most intriguing aspects of quasars, particularly those with inverted spectra, is the role that relativistic effects play in shaping their appearance. In the context of quasars, relativistic effects refer to the strange and often counterintuitive phenomena that occur when objects or radiation move at speeds close to the speed of light. These effects are not merely theoretical, they are observed directly in the behavior of quasars and other high-energy astrophysical objects. When the material around a quasar's central black hole moves at relativistic speeds, it can distort the emission spectrum of the quasar in dramatic ways. This can include the creation of inverted spectra, where certain wavelengths of light are amplified or diminished in ways that defy our standard expectations. Relativistic jets, for example, are one of the most prominent features of quasars. These jets are streams of charged particles that are ejected from the region around the black hole at nearly the speed of light. The material in these jets is often highly magnetized, and as it moves outward, it emits radiation across a broad spectrum. However, because the jets are moving at relativistic speeds, their appearance can be significantly altered by the Doppler effect. When the jet is moving directly toward us, the radiation is blue-shifted, meaning that shorter wavelengths of light are observed. Conversely, when the jet is moving away from us, the radiation is redshifted, with longer wavelengths becoming more prominent. In some cases, the Doppler effect can result in the amplification of certain wavelengths, creating the appearance of inverted spectra. Relativistic beaming is another important factor that contributes to the unique spectra of quasars. This effect occurs when the light from a rapidly moving object is focused in the direction of motion, much like how the headlights of a car appear brighter when the car is moving toward you. In the case of quasars, the relativistic jets are often pointed directly at us, causing a concentration of light that can skew the observed spectrum. Depending on the orientation of the jet and the speed at which it is moving, this can lead to significant variations in the observed spectral lines, which could contribute to the formation of inverted spectra. As we dive deeper into the study of quasars, it's essential to recognize that these objects are not static. They evolve over time. A quasar's spectrum can change as the black hole at its center accretes more material, or as the surrounding environment changes in response to external forces. For example, when a quasar undergoes an outburst, where the rate of material falling into the black hole suddenly increases, this can cause a temporary increase in the brightness and energy output of the quasar. These changes can manifest as variations in the quasar's spectrum, including the possible appearance of inverted spectral features. Over time, as a quasar ages, it may experience a decrease in activity, and the spectrum may become less dramatic, with less pronounced redshift or blue shift. The process of quasar evolution is still not fully understood, and scientists are actively working to uncover the various factors that influence these changes. The role of magnetic fields in quasars is another area that deserves closer attention. Magnetic fields are thought to play a crucial role in the dynamics of quasars, particularly in the acceleration of particles in the accretion disk and the formation of relativistic jets. These magnetic fields are generated by the motion of charged particles within the accretion disk, and they can become extremely strong near the black hole. The presence of such intense magnetic fields can significantly affect the radiation emitted by the quasar, altering the observed spectra in ways that are not yet fully understood. Some researchers believe that these magnetic fields could be responsible for the inverted spectral features seen in certain quasars, as they may influence the acceleration and emission of particles in the jet. In addition to the magnetic fields, the interaction between the quasar and its surrounding environment is another key factor to consider. Quasars are often located in the centers of galaxies, and their powerful radiation can have a profound impact on the gas and dust surrounding them. This interaction can lead to the creation of complex emission lines in the quasar's spectrum, which may be altered by the motion of the material in the accretion disk, or the jet. In some cases, the quasar's radiation may ionize the surrounding gas, causing it to emit light at specific wavelengths. These ionized regions could contribute to the observed inverted spectra, as certain emission lines may be enhanced or suppressed depending on the dynamics of the surrounding material. One of the most exciting aspects of studying quasars and their inverted spectra is the potential for new discoveries that challenge our current understanding of the universe. As we continue to observe and analyze these distant objects, we are likely to uncover new phenomena that we had not previously anticipated. The behavior of matter and radiation near supermassive black holes is still poorly understood, and each new observation brings us closer to unraveling the mysteries of these extreme environments. By studying quasars, we are not only gaining insight into the workings of black holes and the forces that shape them but also learning more about the fundamental laws of physics that govern the universe. The study of quasars and their inverted spectra also has important implications for our broader understanding of the universe's evolution. Quasars are thought to be relics of the early universe, shining brightly in the era when the first galaxies and supermassive black holes were forming. By studying the spectra of quasars at different stages of their evolution, we can gain valuable insight into the conditions that prevailed in the early universe. For example, the light emitted by quasars can help us probe the distribution of gas and dust in the early universe, providing clues about how galaxies and black holes formed and evolved over time. The inverted spectra of certain quasars may provide additional information about the processes that took place in the early universe, offering a more detailed picture of the forces that shaped the cosmos. As technology advances, we are likely to gain even more powerful tools for studying quasars and their inverted spectra. Upcoming space telescopes, such as the James Webb Space Telescope, are expected to provide unprecedented observations of quasars across a wide range of wavelengths. These advanced instruments will allow scientists to probe deeper into the heart of quasars, revealing new details about their spectra, their surrounding environments, and the forces at play within them. With these new observations, we may finally unlock the secrets of the inverted spectra and uncover even more surprising aspects of quasars that we have yet to discover. The study of quasars and their inverted spectra represents one of the most exciting frontiers in modern astrophysics. These distant, enigmatic objects challenge our understanding of the universe, forcing us to reevaluate our models of black holes, galaxies, and the fundamental laws of physics. As we continue to probe the depths of quasars, we are likely to uncover new phenomena that will push the boundaries of our knowledge and transform our understanding of the cosmos. Quasars, with their powerful radiation, intense gravitational fields, and complex spectra, are not just fascinating objects, they are key to unlocking some of the most profound mysteries of the universe. And as we continue to study them, we may find that the answers we seek are even more extraordinary than we could have imagined. As we venture further into the fascinating world of quasars and their inverted spectra, it becomes evident that the deeper we go, the more complex and elusive these cosmic phenomena become. The presence of inverted spectra in some quasars challenges our understanding of not only the fundamental properties of these objects, but also the underlying physical processes that govern their behavior. It's clear that quasars offer us a unique opportunity to explore the extremes of astrophysical science, and as our knowledge grows, so too does our appreciation for the intricacies of these distant, luminous objects. To understand the significance of inverted spectra in quasars, we must delve deeper into the concepts of spectral lines and how they are shaped by the physical conditions in and around quasars. Spectral lines are essentially the fingerprints of different elements and molecules in the universe. When light from a celestial object passes through a prism or a diffraction grating, it spreads out into a spectrum of colors, much like a rainbow. Superimposed on this rainbow are dark lines, known as absorption lines, where light at certain wavelengths has been absorbed by elements in the object's atmosphere or surrounding environment. These lines provide crucial information about the composition, temperature, and motion of the gas and dust in a celestial object. In most cases, these spectral lines appear in a pattern that matches the expectations of basic physics. For example, if a quasar emits light at a particular wavelength, and that light passes through an ionized cloud of gas, certain wavelengths of light will be absorbed by the atoms or molecules in the gas. This results in dark absorption lines in the spectrum at those wavelengths. However, in certain quasars, the spectrum appears flipped. These absorption lines are not just dim but are sometimes completely inverted, with bright emission lines at wavelengths where we would expect to see absorption. This inversion is what makes the spectra of these particular quasars so unusual and puzzling to astronomers. The cause of these inverted spectra is closely tied to the relativistic effects we discussed earlier, especially the interplay between the extreme gravitational fields of quasars and the speed at which material moves around them. The relativistic jets emitted by the black hole at the center of the quasar are not merely points of light. They are incredibly energetic and carry with them the signatures of intense interactions between particles, radiation, and magnetic fields. As material accelerates to relativistic speeds, it emits radiation across a broad spectrum. However, the behavior of this radiation is not straightforward. It is strongly affected by the motion of the emitting material. To understand how this results in inverted spectra, we must consider the Doppler effect in the context of relativistic speeds. The Doppler effect, in simple terms, describes the change in frequency or wavelength of light as the source of the light moves relative to the observer. For example, when a car moves toward you, the sound of its horn becomes higher in pitch, and as it moves away, the pitch drops. In the case of quasars, the relativistic jets often move at speeds approaching the speed of light. When the jet is moving toward us, the light emitted by it is compressed, leading to a shift toward shorter wavelengths. This is known as blue shift. On the other hand, when the jet is moving away from us, the light is stretched out, leading to a shift toward longer wavelengths, known as redshift. However, the situation becomes even more complicated when you consider that the quasar is not a simple point of light. Instead, it is a dynamic system with material moving in all directions, influenced by strong gravitational fields, magnetic fields, and relativistic velocities. In some cases, material in the accretion disk surrounding the black hole may be moving at relativistic speeds in opposite directions, resulting in multiple Doppler shifts that can amplify certain wavelengths and suppress others. This complex interaction of velocities, gravitational effects, and radiation leads to the phenomenon of inverted spectra in some quasars, where certain emission lines are brightened or enhanced rather than absorbed. One of the key challenges in understanding inverted spectra is disentangling these relativistic effects from the more conventional processes of accretion and radiation. In typical quasars, the emission spectrum is dominated by radiation from the accretion disk, where gas and dust spiral in toward the black hole, heating up to extreme temperatures and emitting radiation across a wide range of wavelengths. However, in quasars with inverted spectra, it is likely that the dominant source of emission is not the accretion disk itself, but rather the relativistic jets that are emitted from the region around the black hole. These jets, with their high velocities and complex dynamics, create a unique environment that alters the way we observe the radiation emitted by the quasar. This shift in perspective has led to a number of new theories and models designed to explain the inverted spectra. One such theory involves the concept of the Doppler boosting effect, which occurs when a jet is moving at relativistic speeds toward the observer. In this case, the emission from the jet is not only blue-shifted but also amplified due to the fact that the light is concentrated in the direction of motion. This amplification can cause certain spectral lines to appear brighter, even if they would otherwise be absorbed in a standard quasar spectrum. Additionally, the interaction of the relativistic jet with the surrounding medium can lead to changes in the ionization states of the gas, further complicating the spectrum. Another theory proposes that the inverted spectra may be related to the complex magnetic fields present in quasars. These magnetic fields, which are thought to play a critical role in the formation of relativistic jets, may also influence the radiation emitted by the quasar. Some researchers believe that the interaction between the magnetic fields and the surrounding gas could lead to the creation of hot spots in the spectrum, where emission lines are enhanced due to the high temperatures and energy densities in these regions. These hot spots could be responsible for the inverted spectral features observed in certain quasars. In addition to these theoretical models, the study of inverted spectra also has important observational implications. By examining the spectra of quasars with inverted features, astronomers can gain valuable insights into the physical conditions near supermassive black holes. The intensity, shape, and distribution of spectral lines can provide clues about the temperature, density, and composition of the gas and dust in the accretion disk, as well as the dynamics of the relativistic jets. The study of these spectra also helps to refine our understanding of the physics of black holes, particularly the processes involved in accretion and the formation of jets. Moreover, the inverted spectra of quasars could also have implications for our understanding of cosmology and the early universe. Since quasars are often located at great distances, their light takes billions of years to reach us. This means that when we observe a quasar, we are essentially looking back in time, witnessing the state of the universe as it was in its youth. By studying the spectral features of quasars, including inverted spectra, we can gain insights into the conditions that existed in the early universe, when galaxies and black holes were first forming. This information could help to illuminate the processes that led to the creation of galaxies, stars, and the supermassive black holes that lie at their centers. The study of quasars and their inverted spectra is far from complete, and as our observational techniques improve, we are likely to uncover even more surprises. Upcoming space telescopes, such as the James Webb Space Telescope, are poised to provide us with unprecedented views of quasars, allowing us to explore their spectra in even greater detail. With these new tools, we may uncover additional spectral features that challenge our current theories and open up new avenues of exploration in the study of black holes, accretion disks, and relativistic jets. Quasars with inverted spectra represent one of the most intriguing and mysterious phenomena in modern astrophysics. These objects challenge our understanding of the laws of physics, particularly in the realms of general relativity, high-energy astrophysics, and the dynamics of supermassive black holes. As we continue to study quasars and their spectra, we are not only expanding our knowledge of these extraordinary objects but also uncovering new insights into the fundamental processes that govern the universe. The study of inverted spectra in quasars is just one piece of the larger puzzle, and as our understanding deepens, we may find that the mysteries of the cosmos are even more complex and beautiful than we can currently imagine. As we continue to explore the inverted spectra in quasars, it's essential to consider the broader implications of these phenomena in astrophysics. Quasars, with their intense radiation and remarkable physical properties, provide a laboratory for testing our theories of the universe under extreme conditions. The inverted spectral features observed in these objects offer tantalizing clues about how matter and energy behave near supermassive black holes, where the normal rules of physics are pushed to their limits. To dive deeper into these implications, we must return to the basics of how quasars work. A quasar is a highly energetic and compact region at the center of a distant galaxy, typically dominated by a supermassive black hole. This black hole is surrounded by an accretion disk of gas and dust that is spiraling inward due to the immense gravitational pull. As the gas falls toward the black hole, it is heated to incredibly high temperatures, emitting electromagnetic radiation across the spectrum, from radio waves to gamma rays. The energy released by this process can outshine the rest of the galaxy combined, making quasars some of the brightest objects in the universe. In many quasars, the light emitted from the accretion disk is affected by the strong gravitational fields near the black hole. These gravitational fields warp spacetime itself, bending the path of light and altering the frequency of radiation emitted from the quasar. The result is what we observe as a redshift, or blue shift, depending on whether the emitting material is moving toward or away from us. However, the unusual nature of the inverted spectra comes from the fact that these quasars exhibit features that seem to contradict the expected behavior of light in these environments. The presence of inverted spectral lines suggests that some of the gas surrounding the black hole is not behaving in the typical way we expect. Instead of simply absorbing or emitting radiation at the expected wavelengths, the material in these regions is amplifying certain wavelengths through relativistic effects. As the material moves at speeds close to the speed of light, its motion causes it to emit radiation that is highly directional and amplified in the direction of motion. This is known as Doppler boosting, and is a key factor in the creation of the inverted spectra. However, this is only one piece of the puzzle. The study of inverted spectra also raises questions about the behavior of the accretion disk itself. In many quasars, the disk is not a uniform, static structure but instead exhibits complex interactions between the gas, magnetic fields, and radiation. The presence of strong magnetic fields around the black hole can cause material to become highly magnetized, which in turn can influence the emission of radiation from the quasar. These magnetic fields may interact with the gas in ways that enhance certain wavelengths of light, leading to the observed inverted spectral features. Additionally, the inverted spectra in quasars may also provide insights into the role of the relativistic jets emitted from the poles of the black hole. These jets, which consist of highly energized particles moving at near-light speeds, can carry enormous amounts of energy away from the black hole. The jets themselves are complex structures that interact with the surrounding environment, including the gas and dust in the quasar's accretion disk. These interactions can lead to the amplification of certain wavelengths of light, contributing to the inverted spectra. As we study more quasars with inverted spectra, we continue to refine our understanding of the mechanisms that drive these objects. One of the most intriguing possibilities is that the inverted spectra are the result of an interplay between the relativistic jets and the surrounding accretion disk. This could indicate that the jets are not just passive features but play an active role in shaping the emission from the quasar. The complex dynamics of the jets, the accretion disk, and the surrounding gas may work together to create the inverted spectral features that challenge our current models. The study of these unusual spectral features also has broader implications for our understanding of black holes and the way they interact with their surroundings. For years, scientists have struggled to understand the exact processes that occur near the event horizon of a black hole, the point beyond which not even light can escape. The inverted spectra observed in quasars may provide a window into this mysterious region, offering clues about the behavior of matter and energy under the most extreme conditions in the universe. By studying the spectra of quasars with inverted lines, astronomers can learn more about the properties of the accretion disk, the relativistic jets, and the intense gravitational forces at play. Moreover, the study of inverted spectra could help us better understand the fundamental nature of black holes themselves. Although we cannot observe the black hole directly, the light emitted by the surrounding material provides valuable information about its properties. The presence of inverted spectral features suggests that we may be able to probe the innermost regions of black holes in ways that were previously thought impossible. As our observational techniques improve, we may find that quasars with inverted spectra hold the key to unlocking some of the deepest mysteries of black holes and the nature of gravity. The significance of quasars with inverted spectra extends beyond black hole physics. These objects are often located at great distances, meaning that their light has traveled for billions of years to reach us. This gives quasars a unique role in cosmology, as they serve as time capsules that allow us to look back in time to the early stages of the universe. By studying the spectra of distant quasars, astronomers can gain insights into the conditions of the early universe, when galaxies were forming and supermassive black holes were beginning to take shape. In particular, quasars with inverted spectra may hold important clues about the formation and evolution of supermassive black holes. These objects are believed to have formed early in the history of the universe, possibly within the first billion years after the Big Bang. Understanding how these black holes formed and how they interact with their surroundings is crucial for understanding the growth of galaxies and the large-scale structure of the universe. The study of inverted spectra in quasars may help shed light on the processes that led to the creation of these massive black holes and their role in shaping the cosmos. The discovery of quasars with inverted spectra has already opened up new avenues of research, but there is still much to learn. As our understanding of these objects continues to evolve, so too will our appreciation for the complexity of the universe. The interplay between relativistic jets, magnetic fields, accretion disks, and black hole dynamics is far more intricate than we once imagined. The inverted spectra are not just anomalies but rather manifestations of the extreme conditions that exist near supermassive black holes. As new telescopes and observational techniques come online, we are likely to uncover even more examples of quasars with inverted spectra, providing additional data to refine our models and theories. The James Webb Space Telescope, which is already making groundbreaking observations of distant galaxies, is expected to offer unprecedented views of quasars and their spectral features. This next generation of telescopes will allow us to probe even deeper into the mysteries of the universe, revealing the hidden dynamics of quasars and black holes in greater detail than ever before. The study of inverted spectra in quasars represents one of the most exciting frontiers in modern astrophysics. These enigmatic features challenge our understanding of the most fundamental processes in the universe and offer new insights into the nature of black holes, accretion disks, and relativistic jets. As we continue to explore these extraordinary objects, we are likely to discover even more surprising and unexpected results. The inverted spectra of quasars are not just a curiosity, they are a window into the extreme physics of the universe, offering clues that could help unlock some of the deepest mysteries of space and time. The study of inverted spectra in quasars also highlights the complexity of astrophysical processes and challenges the conventional methods of interpreting distant cosmic phenomena. Quasars are not only fascinating due to their intensity and the magnitude of energy they emit, but they also provide a unique laboratory where we can observe physics in extreme environments. For years, astronomers have observed the usual expected patterns in quasar spectra, but the discovery of inverted spectral features has forced us to reconsider some of our most fundamental assumptions about these distant objects. The core of any quasar, as we know, is the supermassive black hole. It is this incredibly dense object that exerts the immense gravitational pull, drawing in nearby gas and dust into an accretion disk. The energy generated from the friction as this material spirals toward the event horizon of the black hole is what gives quasars their incredible luminosity. Yet the phenomena that produce inverted spectra remain complex and not entirely understood. Part of the challenge is that quasars are located at such vast distances, often billions of light years away, which makes direct observation and interpretation difficult. The light we observe from these distant objects is not only a snapshot of their current state, but also a glimpse into their past. As the light travels across space, it is influenced by the gravitational fields it passes through, a phenomenon known as gravitational lensing. Gravitational lensing occurs when light from a distant quasar is bent and distorted by massive objects, like galaxies or clusters of galaxies, between the quasar and Earth. This effect can alter the appearance of the quasar's spectral features, making them more challenging to interpret. However, even with these complexities, the discovery of inverted spectral features suggests that something more than simple gravitational redshift is at play. The fact that some of the spectral lines are inverted, meaning they are enhanced rather than absorbed, suggests that there are additional processes beyond traditional Doppler shifts and gravitational effects influencing the light we observe. One possible explanation is the role of the broadline region, BLR, in quasars. This region consists of high-velocity gas clouds that surround the accretion disk and are believed to be responsible for the broad emission lines observed in quasar spectra. These lines are typically associated with ionized gas that is moving at speeds ranging from several thousand to tens of thousands of kilometers per second. The interactions between this gas and the radiation from the accretion disk are complex, and it is possible that some of the inverted spectral features observed in quasars arise from the way the broadline region amplifies certain wavelengths of light. The idea of emission line reverberation also provides another potential explanation. This refers to the way that different parts of the broad-line region respond to variations in the quasar's luminosity. The light emitted by the quasar's accretion disk is not constant, and it can fluctuate over time. As the radiation reaches the broad-line region, the gas clouds in this region respond, emitting their own radiation. This emission can sometimes appear to be out of sync with the quasar's primary light, leading to distortions or inverted features in the spectrum. This complex interplay between light and matter may explain some of the inverted spectral features we observe. Another intriguing aspect of quasars and their inverted spectra is the role of the relativistic jets. These high-speed streams of charged particles are often emitted from the poles of the black hole, moving at speeds approaching the speed of light. The relativistic motion of these jets has significant effects on the way light is emitted and observed. Doppler boosting, as previously mentioned, is a critical factor in this process. When we observe a quasar whose jet is pointed toward us, the radiation emitted from that jet is enhanced due to the relativistic motion, resulting in a more pronounced spectral feature. This could contribute to the appearance of inverted spectra, particularly if the jet is emitting more intense radiation in certain wavelengths. The inverted spectra may also reveal important information about the composition and physical properties of the gas surrounding the black hole. In particular, the presence of certain heavy elements in the gas, such as iron and carbon, can lead to absorption and emission features in the spectrum. If the gas is magnetized or subject to intense radiation from the accretion disk or jets, the emission lines can be altered or inverted. This phenomenon is reminiscent of the process known as X-ray reflection, where high-energy X-rays emitted by the quasar are scattered by the surrounding gas, resulting in a spectrum that appears distorted or inverted. What makes the study of inverted spectra particularly intriguing is the potential it offers to test some of the most fundamental theories in physics. The relativistic nature of the phenomena observed in quasars is a direct result of Einstein's theory of relativity, and the presence of inverted spectral features provides a unique opportunity to probe the effects of relativity in extreme environments. The fact that we are able to observe these features from such great distances also provides a new way of testing our understanding of cosmic evolution. As we study more quasars and their spectra, we may begin to uncover patterns and relationships that reveal how black holes, accretion disks, and relativistic jets evolve over time. In addition, the inverted spectral lines could provide new insights into the mechanics of the quasar itself. Quasars are often believed to be in a state of dynamic equilibrium, where the inward gravitational pull of the black hole is balanced by the outward pressure from the radiation emitted by the accretion disk. However, the existence of inverted spectra suggests that this equilibrium may be more complex than we initially thought. The way the gas and radiation interact, the motion of the relativistic jets, and the influence of magnetic fields may all play a role in creating these unusual spectral features. Understanding these interactions could help us better understand the physical conditions near a black hole and how matter behaves under extreme gravitational forces. Furthermore, the study of quasars with inverted spectra opens up new possibilities for observational techniques and tools. The ability to accurately measure and analyze the spectra of distant quasars is a key component of modern astrophysics. Advancements in observational technology, such as the development of more powerful space telescopes like the James Webb Space Telescope, will allow astronomers to obtain even more detailed spectra from distant quasars. These observations will not only help us understand the specific mechanisms that produce inverted spectra, but they will also provide broader insights into the fundamental processes that govern the universe at large. The study of inverted spectra in quasars also has implications for our understanding of the broader universe. Quasars are often used as probes to study the early universe because their light has traveled across vast distances. As such, they can provide valuable information about the conditions that existed when the universe was much younger. The unusual spectra observed in these objects may hold key information about the formation of the first galaxies and black holes. By studying the inverted spectral features, astronomers can gain a deeper understanding of the early stages of cosmic evolution and how the large-scale structures of the universe came to be. The investigation of inverted spectra in quasars is more than just a scientific curiosity. These enigmatic features are a window into the complex processes occurring near the supermassive black holes at the centers of galaxies. They offer a unique opportunity to test our theories of gravity, radiation, and particle physics in the most extreme environments known to exist. As we continue to observe and analyze these distant objects, we are likely to make groundbreaking discoveries that will reshape our understanding of the universe and our place within it. The inverted spectra in quasars serve as a reminder that the cosmos is full of mysteries, many of which we are only just beginning to uncover. With each new discovery, we take another step toward understanding the true nature of the universe and the forces that govern it. As we continue exploring the concept of inverted spectra in quasars, one must consider the implications that such findings have for the study of the universe at large. Quasars, by virtue of their extreme luminosity and the presence of supermassive black holes, are not just beacons illuminating the distant reaches of space but also windows into understanding the most fundamental physical processes. They provide insights not only into the mechanics of black holes and their accretion disks, but they also challenge some of the foundational theories of astrophysics and cosmology. One significant area of study that is linked to inverted spectra involves the energy output of quasars. Typically, the energy emitted by quasars is assumed to be dominated by the radiation from the accretion disk and its surroundings. However, the inverted spectra suggests that additional energy sources may be at work, and the nature of these energy sources could reveal novel phenomena in high-energy astrophysics. The potential involvement of relativistic jets in the emission process is one of the key factors to investigate. Jets in quasars are known to be highly relativistic, meaning they travel at speeds close to the speed of light. These jets can carry enormous amounts of energy, and they might contribute significantly to the inverted spectral features observed in distant quasars. The high-energy radiation from quasars often includes X-rays, gamma rays, and ultraviolet light. The presence of inverted spectral features could suggest that the way light interacts with the surrounding gas and dust is more intricate than previously thought. This could potentially lead to new models of quasar energy production, where the traditional view of radiation coming primarily from the accretion disk is expanded to include contributions from other sources, such as the relativistic jets or from processes deep within the broadline region. These models could have far-reaching implications for our understanding of active galactic nuclei and their evolution over cosmic time. Furthermore, the study of inverted spectra is deeply connected to the role of magnetic fields in quasars. While the precise nature of the magnetic fields in these systems is still under investigation, their presence is known to influence the behavior of the gas surrounding the supermassive black hole. Magnetic fields in the accretion disk and near the black hole are believed to be critical for the generation of relativistic jets, and may also play a role in the way radiation is emitted or absorbed in the quasar. The inversion of spectral lines could be a direct consequence of the complex interaction between the magnetic field and the gas, which alters the emission and absorption processes. This opens up an exciting avenue for further exploration, as understanding the role of magnetic fields in quasars could unlock new insights into high-energy astrophysics and the behavior of matter in extreme conditions. A further intriguing aspect of quasars and their inverted spectra is the potential for feedback mechanisms between the quasar and the galaxy in which it resides. The immense energy output of a quasar can have a significant impact on its host galaxy. The radiation and high-velocity jets emitted by the quasar can blow away gas and dust from the surrounding galaxy, effectively regulating the growth of the galaxy and the black hole at its center. These feedback mechanisms are thought to play a vital role in the evolution of galaxies and the formation of large-scale structures in the universe. By studying the inverted spectral features of quasars, astronomers can gain deeper insight into how these feedback processes operate, and how they influence the formation and evolution of galaxies over cosmic time. Another exciting possibility arising from the study of inverted spectra is the potential to use quasars as probes for studying dark matter and dark energy. Quasars, with their immense luminosity and extreme environments, are ideal objects for testing the properties of dark matter and dark energy, two of the most mysterious components of the universe. While dark matter does not emit, absorb, or reflect light, it does exert gravitational forces, and its presence can be inferred through its influence on visible matter. If the inverted spectral features are indeed caused by the interaction of light with dark matter or dark energy, then quasars could provide a novel means of studying these elusive substances. This is a tantalizing possibility, as the study of dark matter and dark energy is one of the most important ongoing challenges in modern physics. The potential link between inverted spectra and dark matter arises from the idea that dark matter may interact with ordinary matter in subtle ways that affect the behavior of light passing through or around it. In particular, the gravitational influence of dark matter could bend light in unexpected ways, altering the spectral lines we observe from distant quasars. While the role of dark matter in shaping quasar spectra is still speculative, it presents an exciting avenue for future research. As observational techniques improve and more quasars are studied, it may become possible to detect signs of dark matter in quasar spectra, providing a direct observational link between these mysterious phenomena and the larger cosmic structures in which they reside. The study of quasars, and in particular the investigation of inverted spectra, is also leading to advancements in observational techniques. Over the past few decades, telescopes and observatories have made tremendous strides in their ability to observe distant objects with greater precision. Instruments such as the Hubble Space Telescope, the Very Large Telescope, and the upcoming James Webb Space Telescope are enabling astronomers to capture increasingly detailed and high-resolution spectra from quasars. These advancements in technology are essential for unraveling the mysteries of inverted spectra, as they allow for the collection of more accurate data and the development of more sophisticated models to explain the phenomena we observe. The significance of inverted spectra is not limited to quasars alone. The study of these unusual spectral features can also inform our understanding of other astrophysical objects, such as active galactic nuclei, star-forming regions, and even supernovae. The mechanisms that cause spectral inversion are likely to be applicable to a wide range of cosmic environments, and exploring these features could lead to breakthroughs in our understanding of a variety of astrophysical processes. This holistic approach to studying inverted spectra will help us to develop a more comprehensive understanding of the universe and the fundamental forces that shape it. As we continue to study inverted spectra in quasars, we are also building a richer understanding of the broader context in which these phenomena occur. Quasars are part of a larger cosmic web of galaxies, black holes, and dark matter, and their study is intertwined with our efforts to understand the evolution of the universe as a whole. By focusing on the unique spectral features of quasars, we can gain insight into the fundamental processes that drive the formation of galaxies and the cosmic structures that populate the universe. As astronomers continue to probe the depths of space, the mysteries of quasars and their inverted spectra will undoubtedly provide a fascinating and valuable avenue for discovery. The discovery of inverted spectra in quasars is not merely an academic curiosity, but rather a window into the workings of the universe at its most extreme. By challenging our existing models and providing new insights into the behavior of light, matter, and energy in the most hostile environments, inverted spectra are forcing us to rethink some of our most fundamental assumptions about the cosmos. The study of these features is pushing the boundaries of astrophysical research, offering exciting new possibilities for understanding the nature of black holes, relativistic jets, magnetic fields, and even dark matter and dark energy. As we continue to explore the enigmatic world of quasars, the inverted spectra they present may hold the key to unlocking some of the universe's most profound mysteries. It is critical to address how these unusual spectral features can help scientists refine their models of how galaxies, supermassive black holes, and other celestial objects evolve over time. While most of the existing models of galaxy evolution rely on the idea that active galactic nuclei, including quasars, play a dominant role in the regulation of star formation within galaxies, the implications of inverted spectra suggest there may be further intricacies at play in these interactions. For example, inverted spectra could indicate that the processes governing the growth of supermassive black holes are far more complex than previously assumed. The accretion of matter onto a black hole, which is thought to generate much of the radiation emitted by quasars, is typically modeled as a relatively uniform process. However, the presence of inverted spectral features suggests that certain parts of the accretion disk, or its environment, may behave in ways that are not accounted for by traditional models. Understanding these variations could offer valuable insights into the dynamics of black hole growth, the formation of relativistic jets, and the overall evolution of active galactic nuclei. The discovery of inverted spectra also introduces a new layer of complexity when it comes to understanding the role of gas and dust in the vicinity of quasars. Quasars are surrounded by dense clouds of gas and dust, which can absorb, scatter, and re-emit radiation. Typically, this material absorbs certain wavelengths of light, resulting in the characteristic absorption lines we observe in quasar spectra. However, the presence of inverted spectra suggests that these clouds may interact with radiation in unexpected ways, such as by emitting light at the same wavelengths they would normally absorb. This interaction could provide new clues about the temperature, composition, and motion of the gas and dust surrounding quasars, and it may also help us better understand the mechanisms by which energy is transported and dissipated in these environments. Furthermore, the role of relativistic outflows in quasars cannot be underestimated when studying inverted spectra. As we mentioned earlier, quasars are known to produce powerful relativistic jets that extend across vast distances from the central black hole. These jets are believed to carry away energy and momentum, potentially influencing the growth and evolution of the host galaxy. The interaction between these outflows and the surrounding gas and dust may play a critical role in shaping the observed inverted spectral features. For instance, the jet material may interact with nearby gas clouds, causing shifts in the energy levels of the gas and producing inverted spectral lines. This opens up exciting possibilities for the study of quasar feedback mechanisms. Quasar feedback refers to the process by which the energy released by a quasar affects the surrounding galaxy, potentially preventing further star formation or even driving gas out of the galaxy entirely. The inverted spectra observed in quasars could be a direct result of these feedback processes, indicating that the energy and material flowing out from the quasar is altering the properties of the gas and dust in its environment in unexpected ways. By studying these inverted features, astronomers may be able to refine their understanding of how quasar feedback works and how it influences the broader evolution of galaxies. Moreover, the study of inverted spectra in quasars also has profound implications for our understanding of the universe's large-scale structure. Quasars are among the most distant objects we can observe, often located billions of light-years away. This means that the light we receive from these objects carries information about the state of the universe at a time long before the present day. As we peer deeper into the cosmos, we are essentially looking back in time. The study of inverted spectra could provide a valuable tool for probing the early universe and uncovering the physical processes that were at work in the distant past. For example, quasars that existed in the early universe may have different spectral properties than those observed in more nearby systems, offering a glimpse into the changing conditions of the universe over time. The spectral features of these early quasars could reveal important information about the composition of the early universe, the rate of star formation, and the processes that led to the formation of supermassive black holes. Understanding how inverted spectra manifest in these distant objects could help astronomers better constrain the models of early galaxy evolution and the growth of black holes. In addition to these cosmological insights, the study of inverted spectra could also provide a valuable tool for investigating some of the more fundamental aspects of physics, such as the nature of spacetime and the behavior of light in extreme gravitational fields. The unique properties of quasars, with their incredibly powerful gravitational fields and relativistic jets, make them ideal laboratories for testing the predictions of general relativity and quantum mechanics. The fact that inverted spectral features are observed in quasars suggests that the interactions between light and matter in these extreme environments are more complex than our current theories allow for. This opens up an intriguing avenue for further investigation, as researchers look for ways to reconcile our understanding of fundamental physics with the observations made in quasar spectra. Additionally, by studying how light is altered in its journey to reach Earth, scientists may uncover new aspects of cosmological models, including the rate of expansion of the universe. As light travels through vast cosmic distances, it is subject to a variety of influences, including gravitational lensing, redshift, and absorption by intervening material. The presence of inverted spectral features may indicate that there are additional factors at play that have not yet been accounted for in current cosmological models. This could lead to refinements in our understanding of how the universe behaves on the largest scales, including the nature of dark energy and the acceleration of cosmic expansion. The tools and technologies used to observe quasars are continuously improving, and the future holds great promise for unlocking the mysteries of inverted spectra. Observatories like the James Webb Space Telescope, the upcoming Extremely Large Telescope, and other next-generation instruments will allow astronomers to study quasars in unprecedented detail. These advances in technology will help researchers capture higher-resolution spectra, which could reveal even more subtle features in the light emitted by these distant objects. As these instruments come online, we may see significant breakthroughs in our understanding of quasar spectra and the physical processes that shape them. One potential avenue for further research is the role that quantum effects might play in the formation of inverted spectra. The extreme conditions near a supermassive black hole are likely to produce significant quantum mechanical effects, which could influence the behavior of light as it interacts with matter in the accretion disk and surrounding regions. The study of quantum mechanics in such environments could shed light on the fundamental properties of matter and energy under conditions of extreme gravity and temperature. In particular, investigating the quantum nature of light and its interaction with matter in the high-energy regions of quasars could provide new insights into the nature of light itself. The study of inverted spectra in quasars is a field of immense potential that continues to shape our understanding of the cosmos. These enigmatic features offer a window into the extreme environments surrounding supermassive black holes and provide a unique opportunity to test the limits of our physical theories. Whether they are the result of complex interactions between radiation and gas, the influence of relativistic jets, or the effects of dark matter and dark energy, inverted spectra are opening up exciting new avenues of research. As our observational capabilities improve and our models become more sophisticated, the mysteries of quasars and their inverted spectra will likely continue to unravel, offering profound insights into the nature of the universe itself. The study of these distant, powerful objects is not just a journey into the unknown, but a journey that may ultimately help us understand the very fabric of reality. As we continue exploring the significance of inverted spectra in quasars, it is crucial to emphasize how this phenomenon may challenge and refine our understanding of astrophysical processes. The study of quasars has already revealed countless mysteries about the universe, from the nature of supermassive black holes to the interactions between matter and energy in extreme environments. Inverted spectra, however, introduce a new level of complexity, pushing the boundaries of conventional astrophysical models and encouraging us to rethink how we view the fundamental workings of the cosmos. For one, the identification of inverted spectral features suggests that there may be previously unknown types of interactions between light and matter occurring in quasars. Traditionally, scientists have relied on well-established theories of radiation transfer, which describe how light interacts with different types of matter, including the hot gas and dust surrounding a quasar. These models have been highly successful in explaining many of the observed characteristics of quasar spectra, including the broad emission lines associated with the accretion disk and the absorption features resulting from gas clouds intervening along the line of sight. However, inverted spectra indicate that there might be additional physical processes at play that are not fully understood, particularly in regions of the quasar where conditions are extreme, such as near the event horizon of the supermassive black hole. In these regions, the gravitational field is so intense that it significantly alters the way light behaves. As light approaches a black hole, it experiences gravitational redshift. Its wavelength is stretched, shifting it to longer wavelengths. This effect has been predicted by Einstein's theory of general relativity, and it has been observed in various astronomical contexts. However, in the case of quasars with inverted spectra, the behavior of light appears to be more complicated, potentially involving other relativistic effects such as gravitational lensing and Doppler shifting, both of which can distort the light emitted by the quasar. Gravitational lensing occurs when the immense gravitational pull of a massive object, such as a supermassive black hole, bends the path of light from a background source, causing the light to be magnified, stretched, or distorted. This phenomenon has been observed in many contexts, particularly when studying distant galaxies and other celestial objects. In quasars, gravitational lensing may play a role in shaping the observed spectra, including the creation of inverted spectral features. For example, the bending of light around a black hole could cause light from different regions of the accretion disk to follow different paths, leading to the formation of spectral features that appear to be inverted or shifted in unexpected ways. Similarly, Doppler shifting, which occurs when light emitted from a moving source is stretched or compressed depending on the motion of the source relative to the observer, could also influence the observed spectra of quasars. In the case of quasars, where the motion of material in the accretion disk is often relativistic, the Doppler shift could cause significant distortions in the light reaching Earth. The material moving toward the observer would have its light compressed, shifting it to shorter wavelengths, blue shift, while the material moving away from the observer would have its light stretched, shifting it to longer wavelengths, redshift. The combination of these relativistic effects could lead to the formation of spectral features that appear inverted, with certain emission or absorption lines being shifted in ways that are not typical for objects at these distances. These complex interactions between light and matter highlight the need for a more nuanced understanding of quasar spectra. While much progress has been made in the study of quasars, the discovery of inverted spectra serves as a reminder that our models and theories may still be incomplete. To truly grasp the physical processes that govern quasars, scientists must continue to refine their observational techniques, develop more advanced models of radiation transfer, and explore new avenues of research that can shed light on the mysteries of these distant and enigmatic objects. Inverted spectra in quasars also provide an opportunity for scientists to probe the nature of supermassive black holes themselves. The presence of these black holes at the centers of quasars raises important questions about their formation, growth, and role in the evolution of galaxies. Supermassive black holes are believed to form through the accretion of gas and the merging of smaller black holes over time. As they grow, they can release enormous amounts of energy, which can influence the surrounding gas and dust, potentially triggering the formation of stars or, conversely, preventing star formation altogether through the feedback mechanism. The fact that inverted spectra have been observed in quasars suggests that these black holes may be more intricately involved in shaping the surrounding environment than previously thought. One possibility is that the inverted spectral features could be related to the presence of a rotating black hole, or a curved black hole, as opposed to a non-rotating black hole. The rotation of a black hole affects the behavior of the spacetime around it, creating a phenomenon known as frame dragging. This effect causes the spacetime near the black hole to be twisted in the direction of the black hole's rotation, which could influence the behavior of light and matter in its vicinity. In particular, frame dragging could alter the way light interacts with the accretion disk, potentially leading to the formation of inverted spectral features. Furthermore, the presence of a rotating black hole could also play a role in generating relativistic jets, which are often observed in quasars and are thought to be responsible for much of the radiation emitted by these objects. Understanding the relationship between the rotation of black holes and the formation of inverted spectra could provide valuable insights into the mechanics of black hole growth and the dynamics of quasar environments. The idea that inverted spectra could be tied to the rotation of supermassive black holes brings us to an even more intriguing possibility: the connection between these features and the overall spin of the black hole. In astrophysics, the spin of a black hole is an important property, influencing the structure of the surrounding accretion disk, the strength and orientation of relativistic jets, and the overall dynamics of the black hole's environment. The spin of a black hole can be measured by studying the way that light behaves near its event horizon, including the gravitational redshift of light and the presence of X-ray emissions from the inner regions of the accretion disk. Recent observations of quasars have shown that black holes can have a wide range of spins, from slow rotators to rapidly spinning behemoths. The relationship between the spin of a black hole and the spectral features it produces, including inverted spectra, remains an area of active research. It is possible that the spin of a supermassive black hole could play a critical role in shaping the spectral features observed in quasars, including the presence of inverted features. If this hypothesis proves to be true, it could lead to a deeper understanding of how the spin of black holes influences the behavior of matter and energy in their surroundings, as well as how these objects evolve over time. In addition to advancing our understanding of supermassive black holes, the study of inverted spectra could also have important implications for the broader field of astrophysics. The presence of inverted features in quasar spectra may suggest that the interactions between light and matter in extreme environments are far more complex than previously thought. As a result, scientists may need to revise their models of radiation transfer, the behavior of light in strong gravitational fields, and the overall dynamics of active galactic nuclei. Furthermore, the discovery of inverted spectra could help to refine our understanding of the physical processes that occur in other high-energy environments, such as those associated with gamma-ray bursts, pulsars, and other exotic objects in the universe. Ultimately, the study of inverted spectra in quasars is not just about understanding the details of these distant objects. It is about pushing the boundaries of our knowledge of the universe itself. By examining these enigmatic features, scientists can gain insights into the fundamental workings of the cosmos, from the behavior of light in extreme gravitational fields to the growth and evolution of supermassive black holes. Inverted spectra are a testament to the complexity of the universe, and their study will likely continue to yield new discoveries and deepen our understanding of the forces that shape the cosmos. As observational techniques improve and our models of quasar environments become more sophisticated, the mysteries of inverted spectra are likely to be unraveled further, revealing even more about the dynamic processes occurring near the centers of active galaxies. Whether through advancements in telescopes, computational simulations, or the development of new theoretical models, the quest to understand inverted spectra in quasars is sure to be a cornerstone of future astrophysical research. As the study of inverted spectra in quasars progresses, we are likely to encounter even more unexpected results and surprising revelations. These spectra may hold the key to understanding the ultimate mysteries of the universe, offering glimpses into phenomena that are still beyond the reach of current theoretical frameworks. The implications of this phenomenon could be far-reaching, potentially reshaping the way we view the fundamental structure of space-time, the behavior of light, and the interaction between the most extreme objects in the universe. One of the key questions that remains unanswered is why inverted spectra only seem to appear in certain quasars and not in all of them. Given the diversity of quasar types and their varied environments, it's likely that the conditions for the creation of inverted spectra are highly specific. Scientists believe that factors such as the orientation of the quasar relative to Earth, the precise configuration of the accretion disk, the presence of strong magnetic fields, and the rate of material inflow could all influence the appearance of these inverted spectral features. This suggests that the phenomenon could be a result of a unique interplay of variables, where even slight changes in the environment surrounding the quasar could lead to the creation of inverted spectra. For example, it is possible that quasars with particularly high luminosities, those that emit vast amounts of energy, are more likely to produce inverted spectra. These highly energetic quasars may have accretion disks that are more dynamically active, with faster material flows and stronger magnetic fields that alter the behavior of light in ways that are not seen in less active quasars. This would mean that studying the most energetic and brightest quasars could provide the key to understanding the origins of inverted spectra and other unusual spectral features. Another possibility is that the inversion of spectra could be linked to the age or evolutionary state of the quasar. As quasars age and evolve, they go through various stages of activity. In the early stages, the quasar may be in a phase of rapid growth, with vast amounts of gas and dust falling into the black hole, producing intense radiation and energetic emissions. In later stages, the quasar may enter a more quiescent phase, with lower levels of accretion and a calmer environment. The appearance of inverted spectra could be associated with particular stages in this evolutionary cycle, possibly representing a transitional phase where the quasar's activity shifts, or where the surrounding matter undergoes significant changes that affect the emitted light. The role of cosmic dust in the formation of inverted spectra also warrants further investigation. Dust clouds surrounding quasars can scatter and absorb light, distorting the spectral features observed by astronomers. In certain cases, the interaction between light and dust may create unexpected spectral features, including inversions of emission and absorption lines. These dust clouds could introduce additional complexity into the spectrum of a quasar, potentially contributing to the appearance of inverted spectra by altering the light emitted from the central regions of the quasar. Understanding the relationship between dust, gas, and radiation in the environments of quasars is essential for unraveling the origin of inverted spectral features. There's also the possibility that we may be observing phenomena that are occurring in the innermost regions of quasars, regions that are difficult to study due to the extreme conditions involved. The accretion disk surrounding a supermassive black hole is known to be a chaotic environment, with materials swirling at relativistic speeds and experiencing intense radiation. This environment is not only a hotbed for the creation of high-energy radiation but also a place where complex physical processes are at play. Understanding how these processes lead to the creation of inverted spectral features requires new, advanced observational techniques and theoretical models that can account for the full complexity of quasar environments. One promising area of research is the development of more sensitive and precise telescopes that can observe quasars across a broader range of wavelengths. Current telescopes, such as the Hubble Space Telescope, are limited by their ability to observe only certain wavelengths of light, primarily in the optical and ultraviolet ranges. However, new infrared and X-ray telescopes, such as the James Webb Space Telescope, are capable of observing quasars in ways that were previously impossible. By studying the spectral features of quasars in different wavelengths, scientists may be able to identify the specific regions and processes that give rise to inverted spectra, providing more insights into the mechanisms behind this intriguing phenomenon. Additionally, advancements in computational simulations will allow researchers to model the complex behavior of matter and light in the extreme environments of quasars. These simulations can help us understand how various physical factors, such as magnetic fields, the motion of material in the accretion disk, and the effects of relativistic jets, combine to produce the spectral features observed in quasars. By comparing these models with real observational data, scientists can refine their understanding of how inverted spectra form and what they can tell us about the underlying physics of quasars. The study of inverted spectra could also lead to broader discoveries beyond quasars. By understanding how light interacts with matter in the intense environments around supermassive black holes, researchers may gain insights into the behavior of light in other high-energy astrophysical contexts, such as gamma-ray bursts, pulsars, or neutron stars. The processes at play in these extreme environments are often similar to those in quasars, so unraveling the mysteries of quasar spectra could open the door to understanding the broader landscape of high-energy astrophysics. In the long term, the study of inverted spectra could even contribute to our understanding of fundamental physics, especially in the realms of quantum mechanics and general relativity. The behavior of light in the vicinity of supermassive black holes is a testing ground for both of these fields, and any new insights into how light interacts with matter in these regions could help refine our understanding of the fundamental laws that govern the universe. In particular, the study of gravitational lensing, redshift, and other relativistic effects in quasars may provide new opportunities to test theories of quantum gravity, a field that seeks to unify the principles of quantum mechanics and general relativity into a single, comprehensive framework. Moreover, the phenomenon of inverted spectra may eventually contribute to the development of new technologies or techniques for observing the universe. As astronomers continue to probe the most distant and extreme regions of space, they will need increasingly sophisticated instruments that can capture faint, distorted signals from distant quasars and other high-energy objects. The need to detect and interpret inverted spectral features may lead to innovations in telescope design, data analysis methods, and computational techniques, all of which could have far-reaching implications for the field of astrophysics. The study of inverted spectra in quasars represents a fascinating frontier in astrophysics. These unusual spectral features challenge our current understanding of radiation transfer, light-matter interactions, and the behavior of light in extreme gravitational fields. They also raise profound questions about the nature of supermassive black holes, the dynamics of quasar environments, and the fundamental laws of physics. As observational technologies advance and theoretical models evolve, we are likely to uncover even more surprises that will deepen our understanding of these enigmatic objects and their place in the broader cosmos. The discovery of inverted spectra is not just an anomaly, It is a clue that could unlock new insights into the workings of the universe, pushing the boundaries of human knowledge and sparking further exploration of the vast, mysterious universe that surrounds us. As we continue to explore the phenomenon of inverted spectra in quasars, we must consider the broader implications these findings could have on the field of astrophysics as a whole. One such implication involves the way we perceive the structure of the universe. Quasars, which are often located at great distances from Earth, serve as cosmic lighthouses, offering us a unique window into the past and the behavior of matter and energy in some of the most extreme environments in the universe. The study of their spectra, particularly the inverted ones, can offer clues not only to the conditions surrounding black holes but also to the larger structure and dynamics of the universe itself. For instance, understanding inverted spectra could allow us to delve deeper into the interaction between dark matter, dark energy, and the visible universe. While dark matter and dark energy remain largely theoretical, their effects are seen in various aspects of the cosmos, including the motion of galaxies and the expansion of the universe. By examining the spectral signatures in quasars, which lie at the heart of some of the most intense regions of space, scientists may gain new insights into the influence these mysterious forces have on the universe. If inverted spectra are connected to the presence of dark matter or dark energy in some way, this would provide crucial evidence for their existence, potentially bringing us one step closer to understanding these elusive phenomena. Additionally, the behavior of light around supermassive black holes, as indicated by the inverted spectra, could help refine our understanding of the very fabric of spacetime. Black holes are regions of space where gravity is so intense that not even light can escape. This means that the light we observe from a quasar is not only a reflection of the processes taking place at its core but also a result of the extreme warping of spacetime caused by the black hole's gravitational pull. When we see light in the form of inverted spectra, we may be witnessing the bending, stretching, and distortion of spacetime itself. This could offer a direct way of testing Einstein's theory of general relativity, especially in the context of high-energy, high-curvature environments. In fact, the study of inverted spectra in quasars could become a critical tool for understanding the behavior of light in extreme gravitational fields. The study of gravitational lensing, where light from a distant source is bent and magnified by a massive object like a galaxy or a black hole, is already a well-established method of studying the universe. By applying similar principles to the study of inverted spectra, astronomers could develop new techniques for observing and analyzing distant objects, even those located in the farthest reaches of space. This could lead to more accurate models of the universe's large-scale structure, as well as new insights into the formation and evolution of galaxies, stars, and black holes. As we progress in our understanding of quasars, it's important to keep in mind that they are not just cosmic curiosities. They are the key to unlocking many of the mysteries of the universe. The light emitted by quasars is a product of highly complex interactions, and each quasar may hold a different story. The inverted spectra may not be the final chapter of the quasar story but rather a fascinating puzzle piece in the ongoing exploration of the cosmos. As such, they challenge us to rethink our assumptions about the behavior of matter, energy, and light in the universe. Moreover, the study of quasars and their inverted spectra could have practical implications beyond the confines of theoretical astrophysics. Advances in observational technology, driven by the need to study quasars, could lead to breakthroughs in other fields, such as materials science and telecommunications. The cutting-edge techniques used to observe quasars, such as adaptive optics, advanced spectrometers, and high-resolution imaging, may eventually be adapted for use in other industries, contributing to technological innovations that could benefit society in a variety of ways. There are also philosophical and existential implications to consider. The study of quasars and other extreme cosmic phenomena forces us to confront our place in the universe. As we uncover more about the nature of these distant objects, we are reminded of the vastness of the cosmos and the complexity of the forces at play within it. The very idea that light, one of the most fundamental elements of our understanding of the universe, can be inverted, twisted, and distorted by forces beyond our comprehension challenges us to think more deeply about the nature of reality itself. It raises questions about the limits of human knowledge and our ability to truly understand the universe, suggesting that there is much more to discover than we can possibly imagine. The implications for our understanding of time and space are equally profound. Black holes, quasars, and the inverted spectra they produce force us to confront some of the most fundamental questions in physics, such as the nature of time dilation, the structure of spacetime, and the behavior of light near the event horizon of a black hole. These are questions that touch on the deepest aspects of the universe, including the possibility of time travel, the nature of causality, and the limits of human perception. As we continue to probe the mysteries of quasars and inverted spectra, we may eventually uncover new theories that challenge our understanding of time and space, leading to a paradigm shift in our conception of the universe. It is also worth considering the role of future generations of scientists in advancing our understanding of inverted spectra. The field of astrophysics is constantly evolving, and with the launch of new space telescopes and advancements in computational power, the next generation of astronomers and physicists may be the ones to finally crack the code of quasar spectra. They may be able to answer questions that have long eluded us, providing a clearer picture of how quasars and their inverted spectra fit into the broader framework of the universe. As we move forward, the need for collaboration across disciplines will only become more pronounced. Astrophysicists, cosmologists, and physicists must work together, sharing their expertise and insights, to fully understand the implications of inverted spectra and quasars. Furthermore, the involvement of international space agencies and research institutions will be essential in pooling resources and creating the collaborative networks necessary to tackle such a complex problem. The study of inverted spectra is not something that can be achieved by any one team or institution alone. It requires a global effort to bring together the brightest minds and the most advanced technologies. The study of inverted spectra and quasars is not just a quest to understand a peculiar scientific phenomenon. It is part of humanity's larger quest for knowledge and understanding. It is a journey that stretches far beyond the confines of our planet, taking us to the farthest reaches of the universe and challenging us to confront the deepest mysteries of existence. Whether or not inverted spectra lead to the answers we seek, the pursuit of this knowledge is itself an invaluable endeavor. Each new discovery in the world of quasars and cosmic phenomena enriches our understanding of the universe and our place within it, pushing the boundaries of what we know and what we can imagine. As we look ahead, it is clear that the study of inverted spectra and quasars represents only the beginning of an exciting new era in astrophysics. The mysteries surrounding these extreme objects continue to captivate the imagination of scientists and lay people alike, offering new opportunities for discovery and exploration. And who knows, perhaps the answers to the most profound questions about the nature of reality are hiding in plain sight, waiting to be revealed through the study of the most distant, most enigmatic objects in the universe. As we continue to dig deeper into the study of inverted spectra and quasars, we must also consider how these objects challenge the way we think about the very fundamentals of light and matter. The role of quasars in modern cosmology is immense, as they act as markers of some of the universe's most extreme physical conditions. These distant and energetic objects allow us to probe the inner workings of galaxies, the environments around black holes, and the nature of cosmic phenomena that cannot be replicated anywhere near Earth. The study of inverted spectra adds a crucial piece to this puzzle, expanding our knowledge of the universe in ways we might not have imagined. The traditional understanding of light and its behavior, rooted in classical physics, has been fundamentally challenged by these observations. In the early days of astronomy, scientists believed that light behaved predictably, obeying simple laws that governed its movement and interaction with matter. However, with the advent of more powerful telescopes and sophisticated observation techniques, such as those used to study quasars, we have discovered that light behaves in far more complex and mysterious ways. Inverted spectra, in particular, reveal the many different forces that can alter the path and nature of light, pushing our understanding of its role in the universe to new limits. The impact of these findings extends beyond just theoretical physics and astrophysics. They force us to confront long-held assumptions about how the universe operates. For example, the idea of inverted spectra suggests that our understanding of how light interacts with matter in extreme gravitational environments might be incomplete. If the spectral lines are being inverted by unknown forces or interactions that we haven't yet fully accounted for, it could indicate a gap in our current understanding of astrophysics, especially in terms of quantum mechanics and general relativity. Scientists will need to re-examine the underlying assumptions of these two major theories in light of the new evidence presented by quasars and their spectra. Moreover, the inverted spectra challenge our view of the role that black holes play in the cosmos. Black holes have long been thought of as singularities, regions where gravity is so intense that they warp spacetime itself. Quasars, being powered by the intense gravitational forces at the centers of galaxies, are thought to harbor supermassive black holes. As we learn more about these systems and the role of inverted spectra, we realize that black holes are not just passive objects in space but active, dynamic forces that influence everything around them. They are the engines that drive the extreme conditions we see in quasars, and understanding how their gravitational fields distort light is key to unlocking their full significance in the broader context of the universe's evolution. Inverted spectra, therefore, hold the potential to revolutionize our understanding of the behavior of matter and energy under extreme conditions. These spectra may contain hidden information about the processes occurring within quasars, information that could provide clues about the nature of black holes, the formation of galaxies, and the very structure of spacetime itself. For example, the way the light from a quasar bends and shifts could offer a new method for studying the effects of gravity on light, potentially leading to a more accurate model of how black holes bend light and distort spacetime in their vicinity. This could, in turn, allow us to refine our understanding of general relativity, one of the foundational pillars of modern physics. The implications of these findings extend beyond the black hole models we've already established. They open the door to new avenues of exploration that could fundamentally alter our conception of the universe. By studying the inverted spectra, we may gain insights into previously unknown forces, such as the interactions between quantum mechanics and gravity. This could lead to the development of new theories that bridge the gap between general relativity and quantum physics, two of the most important and seemingly incompatible frameworks in modern science. This kind of unification has long been a goal of physicists, and the study of quasars could provide the key to unlocking a more complete theory of everything. This brings us to another critical aspect of inverted spectra in quasars: their potential role in advancing our technological capabilities. The techniques and tools developed for studying quasars and analyzing their spectra have already pushed the boundaries of our observational technology. Instruments like the Hubble Space Telescope, the Very Large Telescope, and various radio telescopes have been used to observe quasars and capture the light they emit. The ongoing development of more advanced instruments, such as next-generation space telescopes and observatories, will only enhance our ability to observe the most distant and extreme objects in the universe. One area where these technological advances could have a direct impact is in the development of new imaging and spectroscopy techniques. As we refine our ability to study quasars in more detail, we may discover new ways to capture light from distant sources with greater precision. Moreover, the study of quasars may inspire new algorithms and data analysis methods that can be applied to other fields, from climate science to artificial intelligence. In this sense, the study of quasars is not just an academic pursuit but could also lead to real-world applications that benefit society in ways we are only beginning to understand. The philosophical questions raised by the study of quasars and inverted spectra are equally significant. As we peer further into the depths of space and time, we are confronted with fundamental questions about the nature of the universe, the limits of human knowledge, and our place within the cosmos. Quasars, with their extreme environments and powerful energy outputs, serve as reminders of how much we have yet to understand about the universe. The light that reaches us from these distant objects carries with it the history of the cosmos, its formation, its evolution, and the ongoing processes that shape its future. By studying quasars, we are essentially looking back in time, observing the universe as it was billions of years ago, and gaining insights into its early history. This sense of cosmic perspective can be both humbling and awe-inspiring, reminding us that we are part of a much larger story. Moreover, the discovery of inverted spectra in quasars forces us to reconsider our assumptions about the fundamental nature of reality itself. If light can be inverted or distorted in ways we don't fully understand, what does this say about our ability to observe and interpret the universe accurately? It raises questions about the limits of human perception and the role of observation in shaping our understanding of the cosmos. In this sense, the study of quasars and inverted spectra is not just a scientific endeavor but also a philosophical one, challenging us to think more deeply about the nature of reality and our place in it. As we look to the future, the study of quasars and their inverted spectra holds enormous promise. The data we have gathered so far has already transformed our understanding of the universe, but much more remains to be discovered. The continued development of advanced telescopes, observatories, and computational tools will allow us to probe these distant and enigmatic objects in unprecedented detail. With each new discovery, we will move closer to unraveling the mysteries of quasars, black holes, and the fundamental forces that govern the universe. The study of inverted spectra may be just the beginning of a new era in astrophysics, one that promises to deepen our understanding of the cosmos and our place within it. As we continue to explore the role of inverted spectra in quasars, the scale and complexity of their importance becomes ever more apparent. These phenomena, though often dismissed as a curiosity, have profound implications for how we understand the very building blocks of the universe. The implications of inverted spectra extend beyond the confines of astrophysics and into the realm of quantum mechanics, relativity, and even philosophy. In this ongoing exploration, it's clear that we're not merely studying distant objects in the sky. We are peering into the very heart of the universe itself, unraveling mysteries that challenge the limits of human knowledge. One of the most intriguing aspects of quasars with inverted spectra is their potential to reveal new insights into the interaction between light and the intense gravitational fields surrounding supermassive black holes. We've long known that these black holes warp spacetime to such an extent that they can bend light and alter its course. However, the discovery of inverted spectra suggests that this bending is far more complex than we once believed. The light emitted by quasars may be influenced by a host of factors that we have yet to fully comprehend. This could be a clue that the standard models of general relativity, which govern how we understand gravity, are not entirely adequate when applied to these extreme environments. The concept of inverted spectra challenges our understanding of how light behaves as it travels through the universe. Typically, when light passes through a medium or gravitational field, it can experience redshift or blue shift, depending on whether it is moving away from or toward an observer. However, in quasars exhibiting inverted spectra, the process seems far more intricate. The typical models we use to describe these phenomena may not be sufficient in these extreme cases. This discovery forces us to rethink the traditional models of light, gravity, and the behavior of matter in highly energetic environments. Furthermore, the inverted spectra observed in some quasars may be indicative of previously unknown physical processes occurring within these objects. Quasars are not merely passive sources of energy. They are incredibly dynamic environments, with complex interactions between matter, radiation, and gravitational forces. In these environments, it's possible that new types of particles, fields, or interactions exist, ones that we haven't yet observed or fully understood. This would mean that the inverted spectra are a signal, a clue to a deeper understanding of the forces at play in quasars. What we see may only be a surface manifestation of the intricate processes occurring within these extreme cosmic laboratories. As scientists continue to study these inverted spectra, it's likely that new theories will emerge to explain them. These theories may involve the development of new models of quantum gravity, which combine the principles of general relativity with those of quantum mechanics. This unification of these two major theories is one of the greatest challenges in modern physics, and the study of quasars with inverted spectra could provide a crucial piece of the puzzle. For example, if we can understand the way in which light behaves in these extreme environments, we might gain new insights into the fundamental nature of space and time. Such insights could lead to breakthroughs that change our entire understanding of how the universe works, from the very smallest scales of quantum mechanics to the largest scales of cosmology. Inverted spectra could also provide valuable clues about the formation and evolution of quasars themselves. Quasars are believed to be powered by the immense gravitational energy produced by supermassive black holes at the centers of galaxies. As matter falls into these black holes, it is heated to incredible temperatures, emitting vast amounts of energy in the process. The discovery of inverted spectra suggests that the energy dynamics within quasars are even more complex than previously thought. It's possible that the spectral inversion is a result of interactions between the matter and radiation surrounding the black hole, or even the black hole itself. Understanding these interactions could help scientists refine their models of how quasars form and evolve over time, offering new insights into the life cycle of these mysterious objects. As we delve further into the study of quasars, we must also consider the role of observational technology in advancing our understanding of these phenomena. The detection of inverted spectra requires incredibly precise measurements of light, using instruments that can capture the faintest signals from distant objects. This has only become possible thanks to advances in telescope technology, including both ground-based observatories and space telescopes like the Hubble Space Telescope and the James Webb Space Telescope. These instruments have allowed astronomers to observe quasars in unprecedented detail, capturing spectra from billions of light-years away. However, as we continue to explore these distant objects, the technology we rely on must also evolve. The next generation of telescopes, such as the extremely large telescopes currently under construction, will provide even more detailed data on the light emitted by quasars. This data will be essential in deciphering the mysteries behind inverted spectra and could lead to new discoveries that we can barely imagine. The study of inverted spectra also highlights the need for collaboration between different branches of science. While astrophysicists are the primary researchers studying quasars and their spectra, the implications of these findings stretch far beyond the realm of traditional astronomy. The insights gained from studying quasars with inverted spectra could have profound implications for fields such as quantum mechanics, particle physics, and even general relativity. Understanding the interaction between light and gravity in these extreme environments could lead to a more unified theory of physics, one that explains both the very small and the very large, from subatomic particles to the vast expanses of the cosmos. The interdisciplinary nature of this research underscores the importance of collaboration between scientists from various fields, who can bring their expertise to bear on the complex questions raised by quasars and inverted spectra. At the same time, the study of quasars also invites us to think more broadly about the nature of scientific inquiry. The discovery of inverted spectra reminds us that the universe is full of surprises, phenomena that challenge our preconceived notions and push us to think in new ways. It is this sense of wonder and discovery that drives scientific progress. Every breakthrough leads to new questions, new mysteries, and new opportunities for exploration. In the case of quasars, the study of inverted spectra is a reminder that there is still so much we don't know about the universe. Each new observation brings us one step closer to uncovering the deeper truths of existence. Ultimately, the study of quasars with inverted spectra is a reminder of the vastness of the universe and the limits of our understanding. It underscores the fact that we are still in the early stages of exploring the cosmos, and there is so much left to discover. While we have made great strides in our understanding of the universe, there is no doubt that we are only scratching the surface. The study of inverted spectra is just one example of how new discoveries can open up entirely new avenues of research, expanding our knowledge and challenging our assumptions. As we continue to explore the universe, one thing is certain: the more we learn, the more we realize how much we still have to uncover. The mysteries of quasars, inverted spectra, and the nature of light and gravity are just the beginning. As we continue to unravel the mysteries of inverted spectra and quasars, the narrative of discovery only deepens. The phenomenon itself serves as a pivotal point in understanding the most extreme astrophysical environments. Not just a quirk of the cosmos, these inverted spectra seem to unlock a window into the very mechanics of quasars and the forces that govern them. Quasars have long been thought of as simple, albeit spectacular, objects, extremely luminous and distant. Yet the discovery of inverted spectra reveals that there is so much more to these cosmic powerhouses than meets the eye. One critical aspect of the inverted spectra that requires deeper exploration is how these spectra provide insight into the nature of black holes and the space-time distortions they create. Quasars, which are often powered by supermassive black holes, offer us a unique vantage point for studying these dark giants. At the center of every quasar is a black hole, whose gravitational pull is so strong that it bends the fabric of space-time itself, distorting the path of light and other radiation. Light from the accretion disk of a quasar, the swirling mass of gas and dust that spirals into the black hole, can take twisted and convoluted paths before it reaches our telescopes. In a typical quasar, the emission lines in the spectrum, the specific wavelengths of light emitted by atoms within the quasar, will either be redshifted or blue-shifted based on the motion of the gas and matter around the black hole. These shifts are understood within the framework of general relativity, which posits that light stretches, redshift, or compresses, blue shift, based on the relative motion between the observer and the source of the light. However, when we observe inverted spectra, we are dealing with a more unusual case. These spectra often display an unexpected reversal in the order of the emissions, with the typical high-energy blue-shifted light turning into red-shifted light, and vice versa. This unexpected inversion challenges traditional models of light behavior and the extreme environments around black holes. The question arises, what causes this phenomenon? Could it be due to the warping of space-time around the black hole, creating conditions where light's travel through space is not only altered but reversed in a way we had not anticipated? Or could it be that there are additional forces or processes at work, new, yet undiscovered aspects of gravity or quantum physics, that are responsible for this spectral inversion? The study of inverted spectra not only deepens our understanding of quasars but also serves as a testing ground for new theories of physics. The quasar environment, where massive gravitational forces and intense radiation fields converge, provides a natural laboratory for studying the interplay between light, gravity, and quantum mechanics. Traditional physics has always maintained that the behavior of light is largely predictable and follows established principles. However, in the case of inverted spectra, we are being presented with a puzzle that does not fit neatly into these preconceived models. To make matters more complex, the role of the accretion disk in quasars may hold key insights into the nature of these inverted spectra. The accretion disk is not a simple, homogeneous structure. Instead, it is a highly dynamic and chaotic environment, with varying temperatures, densities, and magnetic fields. These variations can significantly influence the way light is emitted and how it travels through the accretion disk. It's entirely possible that the interaction between the different regions of the disk could be responsible for the inversion of the spectra. For example, if the light passes through areas of the disk with vastly different properties, say, regions with intense magnetic fields or rapidly rotating material, these interactions could alter the spectral characteristics in ways that we've not yet fully modeled. What's more, the magnetic fields of quasars themselves may play a significant role in the inversion of the spectra. Magnetic fields are a key player in the behavior of matter and light around supermassive black holes, and their presence can significantly distort the radiation emitted by quasars. The role of magnetic fields in the inversion process is an area of growing interest among astrophysicists. Strong magnetic fields may not only alter the emission lines but could also be responsible for creating an environment where the expected relationship between light and gravity is upended. In addition to their implications for the study of black holes, quasars with inverted spectra also push the boundaries of what we know about the universe on a cosmic scale. These objects, which are some of the most distant and energetic sources of radiation we can observe, may be telling us something about the conditions of the early universe. Since quasars are typically observed billions of light years away, their light carries with it a snapshot of the universe as it was in its infancy. The spectral properties of quasars could, therefore, provide us with insights into the conditions that existed shortly after the Big Bang. The inverted spectra observed in these objects might be more than just an oddity. They could represent an opportunity to observe a universe in transition, where conditions are radically different from what we see today. Understanding the precise nature of this inversion could offer crucial clues about the evolution of matter and energy in the universe, shedding light on processes that took place at the very beginning of time. This is not merely a study of distant objects, it is a window into the history of the cosmos itself. For instance, if the inverted spectra are linked to changes in the dynamics of matter and energy in the early universe, then studying them could help us understand how galaxies and black holes evolve over cosmic time. Since quasars are thought to be the most active and energetic regions in the universe, studying their spectra provides us with a unique glimpse into the physical processes that take place in the most extreme environments. Furthermore, this could help us refine our models of cosmic inflation, the theory that explains the rapid expansion of the universe in its first moments. To make sense of the inverted spectra, we must also take into account the broader context of cosmic structure formation. The study of quasars has long been central to understanding the formation of galaxies and the large-scale structure of the universe. Quasars are believed to be the result of the interaction between supermassive black holes and the matter in their surrounding environments. Their light is a record of the complex processes that shape galaxies and their evolution. The discovery of inverted spectra in these objects may be a key to unlocking the mysteries of this interaction. As we continue to examine these distant cosmic phenomena, the role of computational models and simulations will be crucial in advancing our understanding. With each new discovery, scientists are refining their models of black hole accretion disks, gravitational lensing, and the behavior of light in extreme environments. These simulations allow researchers to test different hypotheses about what could be causing the spectral inversions in quasars. By comparing theoretical models with actual observational data, scientists can begin to piece together the complex mechanisms at work. In the coming years, as we gather more data on quasars with inverted spectra, we are likely to see the emergence of entirely new theories that can explain this phenomenon. The implications for the future of astrophysics are enormous. As we expand our ability to observe more distant and more energetic objects, the need for new theories and models will become more pressing. The mysteries of the cosmos, from the deepest black holes to the most distant galaxies, will continue to challenge and inspire scientists to explore the very limits of knowledge. For now, though, the inverted spectra of quasars remain an enigma. They remind us that the universe is full of surprises, many of which we have yet to comprehend. Each discovery is a step forward, bringing us closer to understanding the forces that govern the cosmos. As we stand on the edge of this vast and mysterious frontier, one thing is certain: the more we learn, the more we realize how much more there is to uncover. And in the case of inverted spectra, the story is only just beginning. Relativistic beaming refers to the phenomenon where the intensity and direction of light change due to the high velocity of the emitting source relative to the observer. In the environment of a quasar, where matter accelerates to extreme speeds near the event horizon of a supermassive black hole, this effect becomes substantial. Light emitted from the accretion disk doesn't travel in straight lines, it warps, bends, and sometimes even loops around the black hole before escaping into space. If the geometry is just right, certain emissions can appear dimmer or even inverted depending on how much energy is lost or altered during these interactions. Moreover, the phenomenon of gravitational lensing plays a pivotal role here. When light passes through or near a powerful gravitational field, like that of a black hole, it can bend, split, and even magnify. This lensing effect doesn't just alter where we see light coming from, it can actually change the spectrum we detect. If certain wavelengths are stretched or compressed more than others, it may create the illusion of an inverted spectrum. What we're detecting might not be the actual source signal, but a warped, time-delayed, and transformed version of it, molded by the gravitational topology of space-time. Another compelling theory involves high-energy particle interactions in the quasar's jets. These jets, often shooting out from the poles of the black hole at nearly light speed, are thought to be composed of electrons, positrons, and other particles accelerated by intense magnetic fields. If these particles interact with surrounding radiation in unexpected ways, such as through inverse Compton scattering or synchrotron emission, they could produce unusual spectral lines that mimic inversion. Inverse Compton scattering, in particular, could take lower energy photons and boost them into higher energy X-rays or gamma rays, changing the expected spectral distribution entirely. These models gain further complexity when considering absorption effects. In some quasars, the surrounding gas and dust clouds can absorb specific wavelengths of light, imprinting dark lines in the spectrum. If this absorbing material is irregular, moving, or heated unevenly, it might preferentially obscure parts of the emission spectrum and create an artificial inversion. Even more perplexing is the possibility of negative absorption, where stimulated emission fills in absorption lines, making them appear as emissions. This quantum-level process further blurs the line between classic spectral behavior and inverted observations. What makes this topic so intellectually rich is that inverted spectra aren't just a matter of misinterpretation or error. They could represent an entirely new state of astrophysical interaction. They may signal that some quasars operate under exotic physical conditions that we have yet to replicate or fully simulate. It may be that we're observing phenomena from a vantage point so extreme, whether because of angle, redshift, or relativistic distortion, that traditional laws break down or behave in unexpected ways. Furthermore, the statistical rarity of inverted spectra quasars also opens questions about selection bias and detection limitations. How many such quasars are out there that we simply cannot see due to our instruments being tuned to normal spectra? Could there be an entire subclass of quasars, governed by unknown physics, which we've entirely missed because we weren't looking for these kinds of signals? If our cataloging systems or algorithms are optimized to detect familiar patterns, then inverted patterns might slip past undetected. This suggests that to truly explore the inverted spectrum phenomenon, we may need to design observational tools and algorithms that anticipate the unexpected. In addition to observational astronomy, theoretical astrophysics has taken up the challenge of explaining these anomalies. New simulations, especially those involving magnetohydrodynamic (MHD) modeling of accretion flows and relativistic jets, are being used to replicate the conditions thought to produce inverted spectra. These simulations attempt to account for factors such as magnetic reconnection, shock acceleration, plasma instabilities, and relativistic turbulence, all of which could influence spectral output. In some models, it's not just a black hole or accretion disk dictating the emission profile, but a delicate interplay of magnetic fields, high-energy particles, and distorted space-time working in concert. This search for a comprehensive explanation has even led some theorists to speculate on more exotic ideas, including new particle physics or the interaction of dark matter with high-energy environments. If dark matter interacts weakly but non-negligibly with electromagnetic radiation under extreme conditions, it could conceivably produce distortions in the spectra we observe. While still speculative, these ideas highlight just how far-reaching the implications of inverted spectra could be. Synchrotron emission, on the other hand, results from electrons spiraling around magnetic field lines at relativistic speeds, producing a broad spectrum of radiation that can span from radio waves to X-rays. The complexity arises when this emission interacts with other layers of radiation and matter in the quasar environment. The overlapping of different emission mechanisms, synchrotron, thermal, inverse Compton, can cause spectral signatures to shift, blend, or even cancel each other out in some bands, potentially leading to an apparent inversion of the spectrum. This layering effect becomes especially interesting when considering the orientation of the quasar relative to Earth. Quasars are not isotropic. They don't emit energy evenly in all directions. Much like a flashlight, their emission is often directed along certain axes, particularly through their relativistic jets. If we're observing a quasar at an angle, especially if one of the jets is pointed nearly toward us, we could be seeing a vastly different spectrum than we would from a different angle. This is where the phenomenon known as Doppler boosting comes into play. The radiation from a source moving toward us is compressed, increasing its intensity and frequency. If a jet is aimed directly at us, the light can be significantly blue-shifted, and if there are interactions along that jet pathway, like collisions with surrounding clouds or turbulence, it can rearrange the expected spectral lines. These geometrical and relativistic considerations bring us to another compelling factor: the absorption and reprocessing of light by intervening material. Quasars are not isolated in the vacuum of space. They are surrounded by dust, gas clouds, and often embedded within host galaxies that can absorb certain wavelengths of light and re-emit them at different frequencies. If some regions absorb emission lines and re-radiate energy in a scattered or diffused manner, the original spectral fingerprint of the quasar becomes distorted. In cases where the re-radiated light is stronger in bands where absorption was expected, and weaker where emission should dominate, the result could be perceived as a spectral inversion. But this raises even deeper questions. What does the inverted spectrum tell us about the composition of the intervening material? Could it be that these materials are not ordinary gas and dust as we understand them? There is a possibility that quasars with inverted spectra are signaling the presence of exotic states of matter, high-energy plasmas, ultra-ionized gas, or even forms of matter we have yet to identify. These could be influencing the energy redistribution mechanisms in such a way that they not only warp the spectral lines but create entirely new ones, making the spectrum appear flipped compared to conventional models. This leads us to a more speculative but fascinating avenue of inquiry. What if the inverted spectra are not just observational artifacts or local phenomena, but are indicators of new physical laws at play? Quasars are located billions of light-years away, meaning we're observing them as they existed in the early universe. If their light is inverted in ways that defy standard physics, could that mean that the conditions of the early universe allowed for interactions or particle behaviors that no longer occur? Are these quasars time capsules, revealing physical regimes that existed only during specific epochs of cosmic history? To push this idea further, imagine the implications if inverted spectra hint at variations in fundamental constants, such as the fine structure constant, or the speed of light, over cosmological time scales. If these constants were even slightly different in the past, the way atoms emit and absorb light could be altered, and we would see those changes reflected in the light from ancient quasars. This theory, while controversial, has intrigued some physicists who seek to understand whether the laws of nature are truly immutable, or if they evolved alongside the universe. And then there is the tantalizing prospect of dark matter and dark energy playing a role. Although invisible and undetectable through direct observation, these mysterious components make up 95% of the universe's mass energy content. Could regions of dense dark matter warp or filter light in unknown ways? Might dark energy fields influence how radiation propagates through space, subtly tweaking the spectral profiles of quasars? If so, the inverted spectra may not just be local effects but clues about the underlying structure of the universe on the grandest scales. What makes all of this even more challenging and exciting is the rarity of inverted spectra among quasars. They're not common, which suggests that very specific, perhaps extreme, conditions are required to produce them. This rarity also raises the possibility that we're only beginning to identify them. As our instruments become more sensitive and our sky surveys more comprehensive, it's likely we'll find many more examples. With next-generation observatories like the James Webb Space Telescope, the Square Kilometre Array, and the extremely large telescope coming online, we're on the cusp of a data revolution that could uncover a hidden population of quasars with peculiar spectra. The data from these telescopes will not only provide clearer views of distant quasars, but also deliver unprecedented spectral resolution, allowing scientists to dissect the light with extraordinary precision. We'll be able to map subtle shifts in absorption and emission features, track the movement of gas clouds over time, and identify patterns that could explain how and why spectra become inverted. Machine learning and artificial intelligence will play a pivotal role in this process, analyzing terabytes of data to detect anomalies that the human eye might miss. In this way, the inverted spectra of quasars become more than a strange anomaly, they become a scientific Rosetta Stone. By decoding their messages, we might uncover new layers of reality, uncover unseen forces, and deepen our understanding of how the universe came to be. These peculiar signals from the distant past challenge our models, test our instruments, and spark our imagination. And this is only the beginning. What's more, the chemical composition of the absorbing material plays a critical role. Different elements and molecules absorb and emit light at specific wavelengths. If a quasar's surrounding environment is rich in unusual or exotic elements, or even molecules not typically found in less active regions of the universe, the resulting spectral modifications could be dramatic. Heavy elements like iron or nickel, when highly ionized in extreme conditions, produce complex emission and absorption features that can dominate the spectrum. In certain arrangements, these features might overshadow the typical hydrogen or helium lines, creating an appearance of inversion that defies standard expectations. Additionally, the time variability of quasars adds yet another layer of complexity. Quasars are not static. They fluctuate in brightness, spectrum, and structure over time. Some of these fluctuations occur over days, others over years. These changes can be due to fluctuations in the accretion rate of matter falling into the black hole, or due to instabilities in the surrounding disk, or jets. If we observe a quasar during a particular phase, say, during a sudden burst of high-energy activity, its spectrum might look completely different than it did a year earlier. If we catch such an event at the right moment, we might interpret the spectrum as inverted simply because it doesn't match the quasar's prior or expected state. There is also a significant challenge posed by redshift. Quasars are often billions of light-years away, meaning their light has traveled through vast stretches of expanding space. This journey causes the light to redshift, or stretch to longer wavelengths. However, the universe is not empty. It contains gas, dust, and cosmic structures that the light passes through. Each of these layers can leave their imprint on the spectrum. In some cases, multiple absorption features from different clouds or galaxies along the line of sight can interfere with the clean identification of emission lines, creating patterns that mimic inversion. Beyond these observational factors, some theoretical models propose more exotic explanations. One such idea suggests that quasars might be interacting with dark matter in ways we don't yet understand. If certain forms of dark matter can interact, however weakly, with electromagnetic radiation under extreme gravitational or energetic conditions, it might influence the way quasar light is emitted or travels. This is speculative, but it's an area of increasing interest as more precise observations reveal unexpected spectral features that don't neatly fit within current models. The very architecture of spacetime near a quasar is also a factor worth considering. In the presence of a supermassive black hole, the fabric of space and time becomes distorted. Light paths curve, time dilates, and gravitational redshift becomes significant. The inner regions of the accretion disk, especially those closest to the event horizon, experience intense gravitational fields. Photons climbing out of this well lose energy, and their wavelengths stretch. If some of these photons are partially reabsorbed or bent back toward the disk or jets, it could alter the appearance of the spectrum to an outside observer. In some models, these effects could result in spectral features appearing in reversed order, or at least out of sync with expectations, creating the illusion of inversion. This entire topic is made even more intricate by the presence of so-called broad absorption line quasars, or BL quasars. These are quasars whose spectra contain very broad, blue-shifted absorption lines, typically from highly ionized species. These features indicate the presence of extremely fast outflows of gas, winds moving at thousands to tens of thousands of kilometers per second. These outflows can obscure parts of the continuum emission, create absorption troughs, and reshape the observed spectrum dramatically. If a BL quasar is viewed from a particular angle, its entire emission structure might appear inverted relative to a non-BL quasar, simply due to the dominance of absorption features. Each of these pieces, the relativistic motion, the geometry of observation, gravitational and Doppler effects, intervening matter, chemical complexity, temporal variability, and theoretical possibilities, combine into a grand puzzle. The inverted spectra in quasars may not be a single phenomenon, but rather a constellation of overlapping factors that conspire to produce this enigmatic signature. And even with our most advanced telescopes and computational models, we are still far from fully deciphering their meaning. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.